Tonight, we're going to do something that might fundamentally alter your perception of reality. We're going to journey into the darkest objects in the universe, from black holes, smaller than atoms, to monsters so massive they could swallow 1 trillion solar systems. And along the way, I'm going to show you something that will genuinely change how you understand space, time, and existence itself. You've probably heard of black holes. Maybe you've seen the famous orange donut image from 2019. Or watched a science fiction movie where a spaceship gets sucked into swirling darkness. Perhaps you think of them as cosmic vacuum cleaners, indiscriminately devouring everything around them. Or maybe you imagine them as literal holes in space, tunnels to other dimensions or other universes. All of these ideas contain fragments of truth, but they're also profoundly inadequate. Saying you understand black holes because you've seen a movie is like saying you understand the ocean because you've seen a puddle. The reality is so much stranger, so much more extreme, and so much more beautiful than anything fiction has conceived. Black holes aren't cosmic vacuum cleaners. They don't reach out and grab things from vast distances. They're not instant death portals, though they can certainly kill you in ways that are uniquely horrifying. And they're not holes in space, not in any conventional sense. There's something far more profound. They're places where the fabric of reality itself breaks down, where our best theories admit defeat, where the laws of physics as we understand them simply stop working. The universe isn't just big, it's not even just incomprehensibly vast. When it comes to black holes, the universe spans a range of scales so extreme that the human mind wasn't designed to grasp it. We'll travel from black holes with less mass than a grain of sand, existing for less time than it takes light to cross an atom, all the way to Phoenix A, a monster containing the mass of 100 billion suns, with an event horizon you could measure in light years. That's a span of more than 49 orders of magnitude. To put that in perspective, the difference between an atom and Mount Everest is only about 20 orders of magnitude. The difference between a grain of sand and the entire Earth is only about 25 orders of magnitude. The range of black hole scales is nearly twice the range between the smallest thing you can imagine and the largest thing you've ever seen. This journey will be uncomfortable. Your brain will protest. The numbers will feel meaningless at times. That discomfort you'll feel is not a sign that you're failing to understand. It's the sensation of your mind expanding, stretching to accommodate concepts it was never designed to process. Our brains evolved to understand the distance to the next tree, the weight of a stone, the speed of a running animal. We never needed to comprehend objects whose size is measured in light months. And yet, that's exactly what we're going to attempt tonight. Before we begin this journey, let me ground you in something familiar. Look around the room you're in right now. Maybe you're sitting on a couch, lying in bed, standing in a kitchen. The walls are perhaps 10 to 30 feet away. You can see the boundaries of your space. You understand it completely. This is human scale, the realm where your intuition works perfectly. Now think about your own body. You probably weigh somewhere between 50 and 100 kilograms, somewhere between 100 and 200 pounds. Your body occupies a volume of maybe 70 liters, about the same as a large suitcase. Your density is roughly 1 gram per cubic centimeter, about the same as water. This is why you float, mostly when you swim. Your body is made of atoms, about 7 octillion of them. That's a 7 followed by 27 zeros. Each atom is mostly empty space. The nucleus at the center contains almost all the mass, but it occupies only about 1 trillionth of the atom's volume. If you could remove all that empty space, if you could pack all your atoms together with no gaps, your entire body would be smaller than a grain of dust. You'd still have all your mass, all 70 kilograms, but compressed into a volume smaller than the period at the end of this sentence. This thought experiment isn't just idle speculation. It's the beginning of understanding what black holes are. Because black holes are what happens when you take that compression to its ultimate extreme. When you squeeze matter so tightly that space itself can't support it anymore. When gravity becomes so strong that nothing, not even light, can escape. Let's talk about gravity for a moment. You feel it right now, pulling you toward the center of the Earth. It's keeping you in your chair, holding the atmosphere in place, making water flow downhill. Gravity is the reason Earth is round rather than cube-shaped. It's the reason the Moon orbits Earth, and Earth orbits the Sun. It's the weakest of the four fundamental forces, but it has infinite range and it always attracts, never repels. The strength of gravity depends on two things: how much mass is present and how close you are to that mass. More precisely, it depends on how much mass is concentrated in how small a space. Earth's gravity at the surface gives you a certain pull. If you could somehow compress Earth to half its current radius without changing its mass, the surface gravity would quadruple. Compress it to a quarter of its radius, and surface gravity would increase by a factor of 16. There's a concept called escape velocity. It's the speed you'd need to completely escape a massive object's gravitational pull. On Earth, escape velocity is about 11 kilometers per second, roughly 7 miles per second. If you could throw a baseball at that speed, it would escape Earth's gravity and coast into space forever, never falling back. Of course, you can't throw a baseball that fast. Our rockets can barely manage it, and only with enormous fuel expenditure. The Sun is much more massive than Earth, so its escape velocity is much higher, about 617 kilometers per second. If you were standing on the Sun's surface, which you can't because it's a ball of plasma at millions of degrees, you'd need to reach nearly 200 times Earth's escape velocity just to break free. Now here's the crucial question, the one that leads us directly to black holes. What if gravity was so strong that escape velocity equaled the speed of light? What if an object was so massive, packed into such a small space, that even light itself couldn't escape? This is what a black hole is. It's not an object in the conventional sense. It's a region of space-time where gravity has become so extreme that the geometry of space itself has fundamentally changed. It's a place where Einstein's equations, which describe how mass curves space-time, predict something called a singularity, a point where density becomes infinite and space-time curvature becomes infinite. A place where physics, as we currently understand it, simply breaks down. To understand what this means, imagine space-time as a stretched rubber sheet. This is the classic analogy, and while imperfect, it's useful. Place a bowling ball on the sheet, representing the Sun, and it creates a dip, a curve in the rubber. Planets are like marbles rolling around this dip, following the curved paths created by the Sun's mass. The curvature of the rubber sheet represents the curvature of space-time itself. What we experience as gravity is actually motion along curved space-time. Now imagine a bowling ball, so heavy, so dense, that it doesn't just curve the rubber sheet, it tears through it entirely. It punches a hole that goes down infinitely deep. That's closer to what a black hole represents. It's not just a dent in space-time, it's a rupture, a place where the geometry becomes so extreme that the fabric itself cannot be represented on a simple two-dimensional sheet anymore. The boundary of a black hole is called the event horizon. It's not a physical surface, not a membrane or a wall. It's a mathematical boundary, the point of no return. Once you cross the event horizon, every possible path you could take, every direction you could move, every amount of thrust you could apply, all of them lead inexorably toward the singularity at the center. You can't escape, not because there's some force holding you back, but because the structure of space-time itself has changed. Inside the event horizon, the singularity isn't just in front of you. It's in your future, as inevitable as tomorrow. Think about that for a moment. Outside a black hole, you can move freely in 3 dimensions of space: forward, backward, left, right, up, down. Time marches forward, carrying you from past to future, and you have no choice about that direction. But inside a black hole, something bizarre happens. Time and space swap roles. The singularity is not a place in space that you can avoid by turning left or right. It's a moment in time that you will reach, no matter what you do. Just as you cannot avoid tomorrow, you cannot avoid the singularity. It's in your future, and your future is inevitable. This is why black holes are black. Light that crosses the event horizon can't come back out. No photons escape to reach our telescopes, our eyes, our instruments. A black hole is a region of perfect darkness, surrounded by a spherical boundary where causality itself changes character. The concept of dark stars, objects with gravity so strong that light couldn't escape, was first proposed by an English clergyman named John Michell in 1783. He was working with Newtonian physics, which we now know doesn't quite apply in extreme gravitational fields, but his intuition was remarkably prescient. More than a century later, just months after Einstein published his theory of general relativity in 1915, a German physicist named Karl Schwarzschild found the first exact solution to Einstein's equations. Schwarzschild was serving in the German army during World War I, doing calculations in trenches between battles, while suffering from a painful autoimmune disease that would kill him within months. In this grim setting, he discovered the mathematical description of what we now call a black hole. He sent his solution to Einstein, who was astonished that anyone had found an exact solution so quickly. Schwarzschild died in May of 1916, never knowing that his solution would become one of the most important in all of physics, that his name would be attached to the radius that defines a black hole's event horizon. For decades, physicists debated whether black holes could actually exist in nature, or whether they were just mathematical curiosities that the universe somehow avoided. The term black hole itself wasn't coined until 1967 by physicist John Archibald Wheeler. Before that, they were called frozen stars, or collapsed stars, or sometimes just Schwarzschild singularities. The Soviet physicists, in particular, resisted calling them black holes, partly for linguistic reasons, partly because the term sounded too informal for such a profound phenomenon. But Wheeler's term stuck, partly because it was evocative, partly because it was convenient, and the name captured something essential. These were holes in the observable universe, black voids from which nothing returns. The debate about whether black holes truly existed ended in the 1970s, when astronomers found the first compelling evidence. They discovered X-ray sources in binary star systems, places where intense X-rays were coming from materials spiraling into something compact and invisible. The observations matched exactly what you'd expect if a normal star was orbiting a black hole, with gas being pulled from the star and heated to millions of degrees as it spiraled inward. The first of these, discovered in 1972 and confirmed over the following years, was called Cygnus X1, an X-ray source in the constellation Cygnus. It's about 21 times the mass of the Sun, compressed into a region smaller than a city. Then in April of 2019, something extraordinary happened. The Event Horizon Telescope collaboration, a global network of radio telescopes working together as a single Earth-sized instrument, released the first image of a black hole. Not an artist's illustration, not a simulation, but an actual photograph. It showed a bright orange ring surrounding a dark circle, the shadow of the black hole at the center of the galaxy, Messier 87, some 55 million light-years from Earth. Let me explain what you're seeing in that image, because it's more remarkable than it first appears. 8 radio telescopes, scattered across the Earth from Hawaii to Antarctica to Europe, all observed the same target simultaneously. By combining their data through a technique called very long baseline interferometry, they created a virtual telescope the size of Earth. The resolution was so fine that if you had this telescope in New York, you could read a newspaper in Paris. The orange color you see is not what the black hole actually looks like in visible light. Black holes emit no visible light. By definition, what you're seeing is radio emission translated into visible colors for our eyes. The orange represents radio waves with a wavelength of about 1 millimeter coming from gas orbiting just outside the event horizon. This gas is heated to billions of degrees by friction and magnetic forces. It's glowing in radio wavelengths, and we've colored that glow orange. The bright ring is not uniform. The bottom half is brighter than the top. This is due to relativistic beaming, also called Doppler boosting. The black hole is rotating, and the gas in the accretion disk is orbiting at a significant fraction of the speed of light. Gas moving toward us appears brighter because the light is blue-shifted and concentrated in the direction of motion. Gas moving away from us appears dimmer because the light is red-shifted and diluted. The asymmetry tells us the direction of the black hole's spin. The dark center is the shadow, roughly 2.5 times the diameter of the event horizon. This enlargement is due to gravitational lensing. Photons passing close to the black hole are bent inward by the curved space-time. There's a critical radius called the photon sphere, where light can orbit the black hole in unstable circular paths. Any light emitted inside this radius either falls into the black hole or orbits briefly before escaping. The edge of the shadow corresponds roughly to the photon sphere. What we're seeing is not the event horizon itself, but the region around it where light's trajectory is so warped that it cannot escape outward. 3 years later, in May of 2022, they released a second image, this time of Sagittarius A star, the black hole at the center of our own Milky Way galaxy. These images are proof, direct visual proof, that black holes exist. They're not theoretical anymore. They're real objects, or real regions of space-time, and we've seen them. Every black hole can be described by just 3 numbers: its mass, its spin, and its electric charge. That's it. 3 numbers completely specify a black hole's properties. This is sometimes called the no-hair theorem, because black holes have no distinguishing features, no hair. It doesn't matter if you made a black hole from hydrogen or iron or old television sets or copies of Shakespeare's complete works. Once it's formed, all that information is gone. The chemical composition, the structure, the history, everything erased. Only mass, spin, and charge remain. In practice, the electric charge is almost always negligible. Matter in the universe is electrically neutral on large scales, equal amounts of positive and negative charge. Black holes don't accumulate significant charge, because if a black hole had a net positive charge, it would attract electrons and repel protons until it became neutral again. So charge doesn't play a major role in real astrophysical black holes. That leaves mass and spin as the 2 numbers that really matter. The mass tells you how strong the gravity is, how large the event horizon is, how much energy the black hole can release as things fall in. The spin tells you how fast the black hole is rotating, which affects the space-time geometry around it and enables certain exotic processes we'll discuss later. And from the mass, you can calculate the Schwarzschild radius, the distance from the center where the event horizon forms. For a non-rotating black hole, the event horizon radius is simply proportional to mass. Double the mass, double the radius. The formula involves fundamental constants, the gravitational constant, the speed of light, and the mass of the black hole. But the key insight is that the radius grows linearly with mass. Here's something that might surprise you. For any mass, no matter how small, there's a corresponding Schwarzschild radius. If you could compress the Earth to a radius of about 9 millimeters, about the size of a grape, it would become a black hole. The mass wouldn't change. Earth would still weigh the same 6 trillion kilograms, but compressed to that size, the escape velocity at the surface would exceed the speed of light. The event horizon would form, and Earth would be a black hole. Compress the Sun to a radius of about 3 kilometers, less than 2 miles, and it would become a black hole. All the Sun's mass, enough to make 1 million Earths, crushed into a sphere you could fit inside a city. Compress yourself, all 70 kilograms of you, to a radius of about 10 to the minus 25 meters, far smaller than an atomic nucleus, smaller than a quark, smaller than anything that has physical meaning in our current understanding, and mathematically, you would become a black hole. Your personal event horizon would be so small that quantum mechanics would dominate its behavior. At that scale, our classical description breaks down entirely. Of course, this last example is purely theoretical. There's no known mechanism that could compress a human body or any small object to such densities. Atoms resist compression through electromagnetic forces. Nuclei resist even more strongly through the nuclear force. Below a certain size, quantum effects dominate, and the very concept of size becomes fuzzy. But the mathematics doesn't care whether it's physically possible. The equations simply say, for this mass, this is the radius where the event horizon would form. Nature doesn't have to reach that density. The equations just tell us where the boundary lies. Now that we understand what black holes are, at least in broad strokes, we can begin our journey. We're going to start at the smallest possible scales, in the realm where quantum mechanics and general relativity collide. where our understanding of physics is at its most uncertain. From there we'll climb through more than 40 orders of magnitude, through black holes born from dying stars, through the supermassive monsters at the hearts of galaxies, all the way to the ultramassive titans that strain the very limits of what the universe allows. This journey will take us to places where time and space swap roles, where the past and future have different meanings, where a year of your experience corresponds to millennia passing elsewhere. We'll explore objects that can tear you into atomic threads, and objects so large you could survive inside them for days. We'll confront the limits of human knowledge and the possibility that some questions might have no answers. By the end of this journey, you'll understand why some physicists believe black holes might be the key to understanding reality itself. Why they're not just collapsed stars, but laboratories where the deepest laws of nature are tested. Why they might be gateways to other universes, or time machines to the far future, or the ultimate proof that some things are forever unknowable. You'll also confront questions that have no answers yet. Does the singularity actually exist, or is it a mathematical artifact that quantum gravity will resolve? Can information truly escape from a black hole, or is it lost forever? Could our entire universe be inside a black hole, one bubble in an infinite foam of universes? Do black holes connect to other universes or other times? These questions are not just academic curiosities. They're fundamental to understanding the nature of reality. And black holes are the places where these questions become urgent, where the contradictions in our theories become impossible to ignore. Let's begin where physics itself begins to break down, at the quantum scale, where even the concept of distance starts to lose meaning. The smallest possible black hole is not something you can hold in your hand. It's not something you can see, even in principle. It exists, if it exists at all, only in the mathematical realm where quantum mechanics and gravity meet, a regime where neither of our current theories fully applies. The Planck mass is about 22 micrograms, roughly the mass of a grain of fine sand or a flea egg. It's named after Max Planck, one of the founders of quantum mechanics, and it represents a fundamental scale in physics. A black hole with this mass would have an event horizon at the Planck length, about 1.6 times 10 to the minus 35 meters. This number is so small that it defies comprehension. An atom is about 10 to the minus 10 meters across. An atomic nucleus is about 10 to the minus 15 meters across. A proton is about 10 to the minus 15 meters across. A quark, the constituent of a proton, is smaller than 10 to the minus 18 meters. A Planck length is 20 orders of magnitude smaller than a proton. If a proton were the size of the observable universe, 93 billion light-years across, the Planck length would be about the size of an average tree. At this scale, space-time itself is thought to become grainy or foamy. The smooth geometry that Einstein's equations assume, where you can divide distances into smaller and smaller increments forever, probably breaks down into something discrete, something quantum. Space-time might be made of discrete units, little loops or strings, or some other structures we haven't imagined yet. Imagine zooming in on a photograph. From a distance, it looks smooth and continuous. But zoom in enough, and you see individual pixels. Each pixel is the smallest unit of the image. You can't divide a pixel further and still have meaningful information about the picture. The Planck length might be the pixel size of reality itself. We don't have a theory of quantum gravity yet, so we can't say for certain what happens at the Planck scale. String theory, loop quantum gravity, and other approaches all make different predictions. But they all agree that something dramatic happens. The classical notion of space-time, the idea that you can smoothly divide distances into smaller and smaller increments forever, probably fails. Below the Planck length, concepts like distance and duration might not have meaning in the way we understand them. Virtual particles, predicted by quantum field theory, pop into existence and disappear on timescales related to their energy. The more energetic the particle, the shorter its lifespan. At the Planck scale, quantum fluctuations in the energy of space-time itself become so violent that space-time geometry fluctuates. You'd have microscopic wormholes opening and closing, regions of spacetime with different geometries appearing and vanishing. This is the quantum foam, a seething, probabilistic substrate underlying the smooth spacetime we experience at larger scales. A Planck mass black hole would be the hottest object imaginable. This seems paradoxical. Black holes are cold, right? They're the ultimate heat sinks, absorbing everything and emitting nothing. But in 1974, Stephen Hawking discovered something remarkable. Black holes aren't entirely black. They glow. Hawking radiation is a quantum effect that occurs at the event horizon. The vacuum of space isn't actually empty. It's filled with quantum fluctuations, particle-antiparticle pairs that pop into existence for brief instants before annihilating each other. These virtual particles exist for such short times that they don't violate energy conservation, thanks to Heisenberg's uncertainty principle. Energy can be borrowed from the vacuum for short periods proportional to the amount borrowed. Normally, these virtual particles exist for such short times that they don't have measurable effects. But near an event horizon, something strange can happen. One particle of the pair can fall into the black hole while the other escapes. To an outside observer, it looks like the black hole is emitting particles. The particle that escapes carries energy, which must come from somewhere. It comes from the black hole's mass. The black hole loses a tiny amount of mass energy for each particle that escapes. This process is incredibly slow for large black holes, but rapid for small ones. The temperature of this radiation is inversely proportional to the black hole's mass. Larger black holes are colder. Smaller black holes are hotter. A solar mass black hole has a Hawking temperature of about 12 billionths of a Kelvin, far colder than the cosmic microwave background radiation that fills space, which is currently about 2.7 Kelvin. Such a black hole is actually absorbing more radiation from the universe than it's emitting. It's gaining mass, not losing it. But a Planck mass black hole would have a temperature of about 10 to the 32 Kelvin. That's incomprehensibly hot. The core of the Sun is only about 15 million Kelvin. The hottest temperatures we've achieved in particle accelerators, smashing protons together at near light speed, are around 10 to the 12 Kelvin. The quark-gluon plasma created in these collisions, a state of matter that hasn't existed in the universe since microseconds after the Big Bang, reaches about 4 trillion degrees. A Planck mass black hole would be 20 orders of magnitude hotter than that. At this temperature, the black hole doesn't just glow. It detonates. It releases its entire mass energy in a burst of radiation over a timescale of about 10 to the minus 43 seconds, the Planck time. This is the shortest interval of time that has physical meaning, just as the Planck length is the shortest distance. Events separated by less than a Planck time can't be distinguished, even in principle. Time itself is quantized at this scale. So a Planck mass black hole would form and evaporate essentially instantaneously. It would exist for less time than it takes light to cross its own diameter. It would blink into existence and immediately explode in a flash of radiation carrying the energy of about 500 kilotons of TNT, roughly the yield of a large thermonuclear weapon, all released in an interval of time so short that no physical process we know of could register it happening. Can such black holes exist? We don't know. There's no known mechanism in the present-day universe that could create them. Matter doesn't get compressed to Planck densities in any natural process we're aware of. Even in the cores of neutron stars, where matter reaches nuclear density, about 100 trillion times the density of water, we're still many orders of magnitude away from Planck density. But in the very early universe, in the first fraction of a second after the Big Bang, conditions might have been extreme enough. Density fluctuations in the primordial plasma, tiny variations in the distribution of energy, could have created pockets of matter dense enough to collapse into tiny black holes. The universe was extremely hot and dense immediately after the Big Bang. As it expanded and cooled, different phase transitions occurred, moments when the properties of matter changed dramatically. During these transitions, density fluctuations could have been amplified. These are called primordial black holes, and they're one of the great unsolved mysteries of cosmology. If they exist, If they formed in the early universe, and some of them were massive enough to survive until today, they could account for some or all of the dark matter that we know permeates the cosmos, but have never directly detected. Dark matter is one of the great mysteries of modern physics. We know it exists because we see its gravitational effects. Galaxies rotate faster than they should, based on their visible matter. Galaxy clusters are held together by more gravity than their visible matter can provide. The cosmic microwave background, the afterglow of the Big Bang, has patterns that require dark matter to explain. When we add up all the gravity in the universe, we find that about 85% of the matter is invisible. It doesn't emit, absorb, or reflect light. It interacts gravitationally, but not electromagnetically. What is this dark matter? We don't know. The leading candidates are exotic particles that don't interact with light, things like WIMPs, weakly interacting massive particles, or axions. Decades of experiments have searched for these particles, but so far we've found nothing definitive. Primordial black holes offer an alternative. If a significant fraction of dark matter is actually ancient black holes formed in the first moments of the universe, it would explain the gravitational effects without requiring new particles. But there are constraints. If too many primordial black holes exist, they'd have effects we don't observe. They'd disrupt the cosmic microwave background. They'd lens background starlight in detectable ways. They'd occasionally collide with ordinary matter and produce signals we could detect. Observations rule out certain mass ranges, but there are windows, certain mass ranges where primordial black holes could still exist in significant numbers. Let's move up in scale. Suppose a primordial black hole formed with a mass not of micrograms, but of kilograms or tons. A black hole with the mass of a large asteroid, say 1 billion tons, would have an event horizon about the radius of an atomic nucleus, about 10 to the minus 15 meters. The entire mass of a mountain, 100 billion tons of rock, compressed into a space smaller than an atom. Such a black hole would still emit Hawking radiation, but much more slowly than a Planck mass hole. Its temperature would be about 1 billion Kelvin, hot enough to emit gamma rays, but not hot enough to evaporate quickly. The evaporation rate depends on the temperature raised to the 4th power, so even a modest decrease in temperature dramatically extends the lifetime. A billion-ton black hole would have a lifetime of about 50 billion years, several times the current age of the universe, which is about 13.8 billion years. If one formed in the Big Bang, it would still be around today, slowly radiating away its mass, emitting a faint glow of high-energy gamma rays that would be almost impossible to detect against the background radiation of space. Imagine one of these objects drifting through space. It would be essentially invisible. It doesn't emit visible light, only a faint glow of gamma rays that would be drowned out by cosmic ray background unless you were very close. It's smaller than an atom, so it wouldn't block starlight in any detectable way. It has no magnetic field, no electric charge, no extended structure. It's just a point of intense gravity, drifting silently through the void. It could pass right through the Earth, and we'd barely notice. Let's think through this scenario carefully, because it's both fascinating and eerie. The black hole is moving at some velocity relative to Earth. Let's say something typical for objects in the solar system, maybe 30 kilometers per second, about 20 miles per second. Earth is about 12,700 kilometers in diameter, so the black hole would traverse Earth in about 6 or 7 minutes. As it passes through, it exerts gravitational forces on the surrounding rock and magma. The gravity is strong, but very localized. The gravitational force falls off as the square of distance, so if you're a meter away from this black hole, the force is about 1 trillion times weaker than if you're touching the event horizon. Matter directly in the black hole's path would be pulled inward and absorbed. The black hole would carve a tunnel through Earth, a tube of missing matter about the width of an atomic nucleus. At these scales, matter is mostly empty space anyway. An atom is about 10 to the minus 10 meters across, but its nucleus is only about 10 to the minus 15 meters. That's a factor of 100,000. If an atom was scaled up to the size of a football stadium, the nucleus would be a marble at the center. and the electrons would be tiny dots orbiting near the outer walls. Everything in between is empty space, or more precisely, space filled with the probabilistic electron cloud, but not with solid matter. So most atoms would simply move aside as the black hole passed. The electromagnetic forces between atoms would push them out of the way. The ones that happen to be directly in the path, whose nuclei happen to be within an atomic radius of the black hole's trajectory, would be consumed. They'd fall through the event horizon and be gone. The total mass absorbed would be tiny. Even if the black hole captured every atom in a cylinder with nuclear radius extending through Earth's entire diameter, we're talking about maybe a few micrograms of matter. The black hole entered with a billion-ton mass. It would leave with a billion tons plus a few micrograms, a completely negligible addition to its bulk. But the passage would have effects beyond direct absorption. The sudden gravitational disturbance would generate seismic waves. Think of dropping a stone into a pond. The stone itself displaces a small amount of water, but the ripples spread much farther. Similarly, the black hole's passage would create stress in the surrounding rock. This stress would propagate as seismic waves, like an earthquake, but with a strange signature. Normal earthquakes start at a fault line or subduction zone, usually near the surface or in the crust. The seismic waves propagate outward from that point. But a primordial black hole passing through Earth would create a signal that originated along its entire path, perhaps starting deep in the mantle or even the core, depending on its trajectory. Seismometers around the world might detect an anomalous pulse, a seismic signal that came from inside Earth and propagated outward. The energy release would depend on the black hole's speed and trajectory. It might produce a small earthquake, magnitude 3 or 4, enough to be detected by instruments, but probably not felt by people unless it happened to be very shallow. It would be strange, unexplainable by conventional geology. Geologists would puzzle over it, perhaps attributing it to some unknown tectonic process or a meteor impact they somehow missed. But it wouldn't be catastrophic. Earth would survive. Life would continue. Most people wouldn't even know anything had happened. If you happened to be directly above or below the black hole's path at the moment it passed, you might feel a very brief sensation of extra weight, a momentary increase in gravity lasting a fraction of a second, as if the Earth suddenly pulled harder on you. It would be so brief that your brain probably wouldn't register it consciously. Maybe you'd feel a slight dizziness, a moment of disorientation, and then it would be gone. This scenario is entirely speculative, of course. We have no evidence that primordial black holes exist, let alone that they pass through planets, but the mathematics allows it. And there's a strange beauty in contemplating these tiny monsters drifting through the cosmos, invisible and almost insubstantial, yet containing the compressed remnants of matter from the universe's first moments. They'd be fossils from the Big Bang, time capsules preserving information about conditions in the first microseconds of cosmic history, forever beyond our reach, forever unknowable, unless we happen to detect their faint radiation or observe one passing through a star or planet. As we continue up the mass scale, we encounter a strange gap. There's no known way to make black holes between about 1 solar mass and about 5 solar masses. This desert in mass space tells us something important about how stars work and how they die. It's a clue to the physics of stellar collapse, to the mechanisms that determine whether a dying star becomes a neutron star or a black hole. Stars are fusion reactors, converting hydrogen to helium in their cores, releasing energy that provides the pressure to support them against their own gravity. As long as fusion continues, the star is stable. The outward pressure from fusion balances the inward pull of gravity. But fusion has limits. You can fuse hydrogen into helium, helium into carbon and oxygen, carbon into heavier elements, all the way up to iron. Each step releases energy, but each step requires higher temperatures and pressures than the last. Iron is the end of the line. Iron has the most tightly bound nucleus. Fusing iron into heavier elements doesn't release energy. It consumes energy. When a massive star builds up an iron core, fusion stops. There's no more energy generation to support the star. The core, suddenly lacking pressure support, collapses. What happens next depends on the mass. For stars below about 8 solar masses, The core collapse is halted by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too close together. The Pauli exclusion principle, one of the fundamental rules of quantum mechanics, says that no two fermions, particles like electrons, protons, or neutrons, can occupy the same quantum state. When electrons are compressed, they're forced into higher and higher energy states, and this creates a pressure that resists further compression. The result is a white dwarf, an object about the size of Earth, but with the mass of the Sun, supported not by fusion, but by quantum pressure. White dwarfs can't exceed about 1.4 solar masses. This is the Chandrasekhar limit, calculated by Subramanian Chandrasekhar in the 1930s, when he was a graduate student on a ship from India to England. Above this mass, electron degeneracy pressure isn't enough. Gravity overwhelms the quantum pressure, and the core collapses further. For stars between about 8 and 20 solar masses, the collapse compresses electrons and protons together, forcing them to combine through a process called electron capture. An electron and a proton combine to form a neutron and a neutrino. The neutrino, which barely interacts with matter, escapes at nearly the speed of light, carrying away energy. The neutrons remain, and they're packed together at nuclear density. The result is a neutron star, an object about 20 kilometers across, but with a mass between 1 and 3 solar masses. Neutron stars are supported by neutron degeneracy pressure, which is much stronger than electron degeneracy pressure because neutrons are much more massive than electrons. But neutron degeneracy pressure also has a limit, called the Tolman-Oppenheimer-Volkoff limit, somewhere around 2 to 3 solar masses. We don't know the exact value because it depends on the properties of matter at nuclear densities, which we can't yet measure or calculate precisely. The equation of state for neutron star matter is uncertain. At normal densities, we understand how matter behaves. Atoms interact electromagnetically. We have good models. At nuclear densities, where neutrons are touching, the nuclear force dominates. We understand this reasonably well from nuclear physics experiments. But inside neutron stars, the density might be even higher than atomic nuclei. Neutrons might break down into quarks. Other exotic particles might appear. The strong force behaves differently at these energies. We're extrapolating beyond what we can test in laboratories. But we know there's a limit. Above that limit, nothing can stop the collapse. No known force or pressure can counteract gravity. The core collapses past the neutron star stage, past every possible resistance, and a black hole forms. This happens for stars above about 20 solar masses. The core collapses to a black hole in less than a second. The outer layers, no longer supported by the core, fall inward and then rebound in a cataclysmic explosion called a supernova. For a few weeks, the supernova can outshine an entire galaxy. But at the center, hidden behind the expanding debris, there's already a black hole. Let me paint this picture more vividly, because the death of a massive star is one of the most dramatic events in the universe. The star has spent millions of years fusing elements in its core. It started with hydrogen, the simplest element, fusing it into helium. This phase lasted millions of years, providing steady energy output. When the hydrogen in the core was exhausted, the core contracted and heated up until it was hot enough to fuse helium into carbon and oxygen. This phase lasted perhaps 100,000 years. Then carbon fusion began, creating neon and magnesium. This phase lasted a few hundred years. Then neon fusion, lasting about a year. Then oxygen fusion, lasting several months. Then silicon fusion, the final stage before iron, lasting about 1 day. With each stage, the core contracts, heats up, and the fusion becomes more frantic, burning through fuel faster and faster. Finally, the core is iron. Iron nuclei, the most stable form of matter in the universe, sit at the center of the star. The star tries to fuse them, but it can't. Each fusion reaction absorbs energy instead of releasing it. The core cools slightly. The pressure drops. Gravity squeezes harder. The core contracts. Then, suddenly, catastrophically, the core collapses. In about a quarter of a second, the core shrinks from the size of Earth to the size of a city. The temperature spikes to hundreds of billions of degrees. Photons are so energetic that they break apart iron nuclei, reversing all the fusion that built them. This process absorbs enormous amounts of energy that had been supporting the core. The support vanishes. Electrons are forced into protons, forming neutrons and releasing neutrinos. In about 1 second, the collapsing core releases more energy in neutrinos than the Sun will produce in its entire 10 billion-year lifetime. The neutrinos, which barely interact with matter, stream outward at the speed of light. Most pass through the star without interacting. But a tiny fraction of a percent, are absorbed by the outer layers. Their energy is so enormous that even this tiny fraction is enough to reverse the infall of the outer layers. The outer layers rebound. They're accelerated outward at speeds of tens of thousands of kilometers per second, fast enough to escape the star's gravity. They slam into the surrounding space, creating a shock wave that heats gas to billions of degrees. The star explodes. Its brightness increases by a factor of 1 billion in a matter of hours. For a few weeks, it can outshine its entire galaxy, but at the center, the core is already gone. If the original star was massive enough, if the core exceeded the Tolman-Oppenheimer-Volkoff limit, the core didn't stop collapsing at neutron star density. It kept going. Neutron degeneracy pressure couldn't hold it. The core collapsed through the Schwarzschild radius. An event horizon formed. The singularity, whatever that truly is, came into existence. The black hole is born in a fraction of a second, long before the outer layers explode. From the black hole's perspective, if it has a perspective, the explosion happens in slow motion, red-shifted and time-dilated. From the explosion's perspective, the core vanishes, simply ceases to exist in the observable universe, leaving behind a region of curved space-time that can never be seen again. Stars between about 8 and 20 solar masses are in a transition zone. Some become neutron stars. Some, if conditions are right, might form black holes. The exact boundary depends on the star's mass, its composition, its rotation rate, and probably other factors we don't fully understand. But stellar evolution models suggest there should be very few black holes in the range from about 2 to 5 solar masses. This is the mass gap, and only recently have we started finding objects that might fill it. The smallest stellar mass black holes we're confident exist are around 5 solar masses. Let's take that as our baseline and really try to understand what it means. A 5 solar mass black hole has an event horizon radius of about 15 kilometers, roughly 9 miles. The event horizon is a sphere, so the diameter is about 30 kilometers, about 19 miles. That's about the size of a large city. Manhattan is about 21 kilometers from its northern tip to its southern tip, about 13 miles. This black hole would fit comfortably within the boundaries of a metropolitan area. But here's the part that breaks your brain. This object contains 5 times the mass of the Sun. The Sun is huge. It's a ball of plasma with a diameter of about 1.4 million kilometers, about 864,000 miles. You could fit about 109 Earths across the Sun's diameter. You could fit about 1.3 million Earths inside the Sun's volume. The Sun contains 99.86% of all the mass in our solar system. Everything else, all the planets, all the moons, all the asteroids and comets, all of it together makes up less than 0.2%. This black hole contains the mass of 5 million Earths, compressed into a volume that you could walk across in a few hours if there were anything to walk on, which there isn't. If you could somehow stand at the event horizon of a 5 solar mass black hole and look across to the opposite side, it would be visible on the horizon, about 30 kilometers away. That's the distance you might drive to visit a neighboring town. Let's think about what this means in terms of density. The event horizon is not a physical surface. Remember, it's just the boundary where escape velocity equals the speed of light. But we can still calculate an average density by dividing the mass by the volume inside the event horizon. For a 5 solar mass black hole, the average density inside the event horizon is about 2 billion kilograms per cubic meter. For comparison, water has a density of 1,000 kilograms per cubic meter. Steel has a density of about 8,000 kilograms per cubic meter. The densest naturally occurring element, osmium, has a density of about 22,000 kilograms per cubic meter. White dwarf material has a density of about 1,000,000 kilograms per cubic meter. Neutron star material has a density of about 100 trillion kilograms per cubic meter. The average density inside this black hole's event horizon is 2 million times the density of water, about 100,000 times the density of the densest metal, about 20,000 times the density of a white dwarf, but still less than the density of a neutron star. A teaspoon of matter at this average density would weigh about 10,000 tons, the weight of a large naval ship. But this is just the average. The actual singularity at the center has infinite density, at least according to general relativity. All the mass is compressed into a single point with zero volume. Divide any finite mass by zero volume and you get infinity. Infinity is usually a sign that your theory has broken down, and that's exactly the case here. We don't believe the singularity is actually infinite. We think quantum effects must modify the picture somehow, but we don't know how, because we don't have a quantum theory of gravity. If you could somehow approach a 5 solar mass black hole, the tidal forces would kill you long before you reach the event horizon. Tidal forces are the difference in gravitational pull between different parts of your body. Your feet are slightly closer to the black hole than your head, so they experience slightly stronger gravity. Normally, on Earth, this difference is tiny, completely negligible. Even orbiting Earth on the International Space Station, the tidal forces on your body are imperceptible. But near a black hole, tidal forces become extreme. For a 5 solar mass black hole, if you were falling in feet first, the tidal force would become lethal at a distance of about 200 kilometers from the event horizon, more than 10 times the horizon radius. At that distance, your feet would be pulled with thousands of times more force than your head. The difference would be strong enough to overcome the molecular bonds holding your body together. The tensile strength of human tissue, the ability to resist being pulled apart, is measured in megapascals, millions of pascals of pressure. At 200 kilometers from the event horizon, the tidal stress on your body would exceed 1,000 megapascals, far beyond what any biological tissue can withstand. You'd be stretched like taffy, elongated into a thin stream. This process has a technical name in the physics literature: spaghettification. It's a gruesome way to die. Your body would be torn apart, not in some quick, catastrophic rupture, but in a progressive stretching. Your skeleton would separate vertebra from vertebra. The ligaments holding your bones together would tear, your muscles would pull apart, your tissues would rupture, your circulatory system would break down. Blood vessels tearing as the distance between your heart and extremities increased beyond what your vascular system could span. And all of this would happen while you were still conscious, at least for the first few seconds. Pain signals travel through your nervous system at speeds up to about 100 meters per second. The disruption would propagate through your body as a wave. You might have several seconds of consciousness, experiencing your body's destruction in real time, feeling the pulling sensation intensify, feeling your bones separate, feeling your internal organs rupture, before the signals from your lower body stopped reaching your brain because the nerve connections were physically severed. Eventually, you wouldn't be recognizable as human. You'd be a stream of tissue, then a stream of cells, then a stream of molecules. If the tidal forces continued to grow, which they would as you got closer, eventually even the molecules would be torn apart. Atoms would be separated. Then atomic nuclei would be torn from their electrons. At the event horizon itself, the tidal forces for a 5 solar mass black hole are strong enough that even atomic nuclei might be disrupted. And that's assuming you survive the radiation environment, which you wouldn't. Real black holes, especially those in binary systems feeding on a companion star, are surrounded by accretion disks of superheated matter. The material in these disks is heated to millions of degrees by friction as it spirals inward, colliding with other material, compressing and heating through the conversion of gravitational potential energy to thermal energy. At these temperatures, the gas emits intense X-rays and gamma rays. The radiation intensity near an active black hole is lethal at distances of thousands or millions of kilometers, depending on the accretion rate. You'd be irradiated and vaporized long before tidal forces could spaghettify you. Your body would absorb so much high-energy radiation that you'd essentially boil from the inside out, your tissues breaking down at the molecular level. But let's ignore those practical concerns and imagine you somehow survive long enough to watch someone else fall into the black hole while you remain at a safe distance, perhaps in a heavily shielded spacecraft, far from the event horizon. What would you see? You'd see them fall faster and faster as they approach the event horizon. Their velocity would increase as they converted potential energy to kinetic energy. But as they got closer to the horizon, something strange would happen. They'd appear to slow down. Their motion would become sluggish. They'd approach the horizon asymptotically, getting closer and closer, but never quite reaching it. This is time dilation, a consequence of Einstein's theory, one of the strangest predictions of general relativity. Clocks in strong gravitational fields run slower when viewed from farther away. As your companion approaches the event horizon, where the gravitational field is strongest, their clock slows down relative to yours. 1 second on their clock might correspond to 2 seconds on yours, then 10 seconds, then 1,000, then 1,000,000, approaching infinity as they approach the horizon. They'd become redshifted. The light from their body, reflected sunlight, or light from their spacesuit would stretch to longer wavelengths. Electromagnetic waves are stretched when they climb out of a gravitational field. The deeper the field, the more the stretching. Near the event horizon, the redshift becomes extreme. Visible light shifts toward the red end of the spectrum, then into infrared, then into microwaves, then into radio waves, then into wavelengths so long that no detector could register them. They darken and fade. The photons leaving their body become less and less energetic and also less frequent. Photons emitted near the horizon take longer and longer to reach you because they're climbing out of an increasingly deep gravitational well. Asymptotically, they'd appear to freeze at the event horizon, getting dimmer and dimmer, redder and redder, but never quite crossing. The last photon they emit before crossing the horizon would take an infinite amount of your time to reach you. From their perspective, everything would be completely different. They'd feel themselves accelerating. They'd see the event horizon approaching, and they'd cross it at a definite moment in their own time. From their point of view, nothing special happens at the horizon. It's not marked. There's no surface, no barrier, no sensation. They'd simply pass through, not realizing until it was too late, until they tried to turn back or send a signal outward that they'd crossed the point of no return. Both perspectives are correct. Both are equally valid descriptions of reality. This is what relativity means. There is no absolute time, no universal now that all observers agree on. Your experience and their experience are both real, both true, and yet completely incompatible. They cross the horizon in their time. They never cross the horizon in your time. Reality itself depends on the observer. This isn't some philosophical abstraction. It's a measurable, testable, confirmed prediction of general relativity. When GPS satellites orbit Earth, their clocks run slightly faster than clocks on the ground because they're in a weaker gravitational field. The difference is only about 45 microseconds per day. But if we didn't correct for it, GPS positioning would be off by kilometers within days. Every time you use GPS navigation, you're relying on calculations that account for general relativistic time dilation. Near a black hole, these effects are magnified enormously. Time dilation isn't a subtle correction, it's the dominant phenomenon. An astronaut orbiting close to a black hole's event horizon might experience a year of subjective time, while decades or centuries pass in the external universe. This is real. This is how space-time works. This 5 solar mass black hole, despite its relatively small size, would persist for an almost inconceivable length of time. Its Hawking temperature is about 12 billionths of a Kelvin, far colder than the cosmic microwave background, which is currently about 2.7 Kelvin. The black hole is actually absorbing more radiation from space than it's emitting. It's growing, not shrinking, by a tiny amount each year. Only in the far future, after the universe has expanded enough that the cosmic microwave background has cooled below 12 billionths of a Kelvin, will the black hole start to evaporate. The universe will need to expand by a factor of about 200 million. At the current expansion rate, accounting for dark energy and the accelerating expansion, this will take trillions of years. By that time, all the stars will be dead. The last red dwarfs will have exhausted their fuel. The universe will be dark except for the faint glow of white dwarfs and neutron stars, and eventually, even those will fade. And even then, even after the black hole starts losing mass to Hawking radiation, the process is incredibly slow. The lifetime of a 5 solar mass black hole due to Hawking radiation is about 10 to the 67th years. That's a 1 followed by 67 zeros. 10,000 trillion years. To put this in perspective, the current age of the universe is about 14 billion years, which is about 10 to the 10th years, about 10 billion years. The black hole will last 10 to the 57 times longer than the current age of the universe. If you started counting seconds at the Big Bang and counted one number per second without stopping, you'd reach about 400 billion by now, which is still only about 10 to the 11th. You'd need to count for 10 to the 56 times longer than the current age of the universe just to count the number of years this black hole will last. By the time this black hole evaporates, the last stars will have burned out trillions of years earlier. Stellar mass black holes will be the last large objects in the universe. They'll slowly evaporate, radiating away their mass as Hawking radiation, while the universe expands around them. And even then, we'll have barely started waiting for them to disappear. Let's move up in mass. A 20 solar mass black hole has an event horizon radius of about 60 kilometers, roughly 37 miles. This is roughly the size of a large metropolitan area. The Los Angeles metropolitan area is about 75 kilometers across. This black hole would fit comfortably in a region the size of a major city. One of the most famous stellar mass black holes is Cygnus X1, about 21 solar masses, located about 6,000 light-years from Earth. It was discovered in 1964 as a powerful source of X-rays and confirmed as a black hole over the following years through careful observations of its orbital companion, a blue supergiant star. The story of Cygnus X1's discovery is a fascinating chapter in the history of astronomy. In the early 1960s, X-ray astronomy was just beginning. Instruments on sounding rockets, brief suborbital flights that reached the edge of space for a few minutes, detected X-rays coming from various points in the sky. One of the strongest sources was in the constellation Cygnus. Optical telescopes identified a blue supergiant star at that location, but the star itself couldn't be producing the X-rays. It was the wrong type. Further observations revealed that the star was wobbling, moving back and forth in a regular pattern with a period of 5.6 days. The star was orbiting something massive but invisible. By measuring the star's orbital velocity and applying Kepler's laws, astronomers calculated the mass of the invisible companion. It was about 20 solar masses, far too massive to be a neutron star. The only explanation was a black hole. But at the time, many physicists were skeptical that black holes actually existed. The prominent physicist Kip Thorne was confident that Cygnus X1 was indeed a black hole. The equally prominent Stephen Hawking was skeptical. In 1975, they made a bet. The stakes were whimsical but meaningful. A subscription to Penthouse magazine if Hawking won, a subscription to Private Eye if Thorne won. Over the following years, evidence accumulated. Better observations, better instruments, better theoretical understanding, all pointed to Cygnus X1 being a black hole. In 1990, Hawking conceded the bet, traveling to Thorne's office to sign the bet statement, admitting defeat. He later said he'd made the bet as a kind of insurance policy. If black holes didn't exist, at least he'd get a consolation prize. Cygnus X1 is part of a binary system. The black hole and the blue supergiant star orbit their common center of mass every 5.6 days. The star is so close to the black hole that the black hole's gravity pulls gas from the star's outer layers. The star has an extended atmosphere, and the outermost layers are only loosely bound. The black hole's gravity tugs at these layers, pulling streamers of gas toward itself. This gas doesn't fall directly into the black hole. It has angular momentum, inherited from the star's rotation and orbital motion. Conservation of angular momentum means the gas can't spiral straight in. Instead, it spirals inward, forming an accretion disk. The accretion disk is a masterpiece of extreme physics. The gas in the disk orbits at tremendous speeds, a significant fraction of the speed of light in the inner regions. At the event horizon, material is orbiting at nearly the speed of light. A bit farther out, at 3 times the Schwarzschild radius, material can orbit stably at about 40% of light speed. These are the fastest stable orbits possible around a non-rotating black hole. Friction between adjacent layers of gas heats the material to millions of degrees. Different parts of the disk orbit at different speeds, with inner material moving faster than outer material, just like planets closer to the Sun orbit faster than planets farther out. This differential rotation creates shear, and shear creates friction. The gas rubs against itself, converting kinetic energy to heat. At millions of degrees, the gas emits X-rays. The X-ray spectrum tells us the temperature, the density, the composition. We can map the accretion disk by analyzing the X-rays. We see emission from iron atoms, highly ionized because the temperature is so high that electrons have been stripped away. The ion emission is broadened and distorted by the Doppler effect from the orbital motion and by gravitational redshift from the black hole's gravity. The efficiency of this process is staggering. When gas falls into a black hole through an accretion disk, about 10% of its rest mass energy is converted into radiation. This is Einstein's famous equation, E equals mc squared, in action. Mass is energy. When matter falls into a strong gravitational field, it releases energy. In an accretion disk, this energy is released gradually, as the matter spirals inward, heating up through friction and compression. Compare this to nuclear fusion, which converts about 0.7% of mass to energy. Fusion powers the sun and all stars. It's the most efficient energy source we've mastered on Earth. But accretion onto a black hole is more than 10 times more efficient. Black holes are the most efficient engines in the universe for converting mass into energy. This efficiency has profound implications. A single solar mass of material falling into a black hole through an accretion disk releases more energy than the sun will produce over its entire 10 billion-year lifetime. This is why active galactic nuclei, powered by supermassive black holes consuming matter, can outshine entire galaxies containing hundreds of billions of stars. The black hole isn't more massive than the galaxy, but it's converting mass to energy far more efficiently than stars do. At a 20 solar mass scale, tidal forces at the event horizon are still lethal, but less extreme than for a 5 solar mass hole. The tidal force is inversely proportional to the square of the black hole's mass. A 20 solar mass black hole has 16 times weaker tidal forces at its event horizon than a 5 solar mass black hole. You'd still be spaghettified, but perhaps at the event horizon itself, rather than far outside it. It's a small comfort. Either way, you don't survive the encounter, but the difference matters for what happens to matter falling in. Stars or planets passing close to a 20 solar mass black hole might survive closer approaches than they would near a 5 solar mass black hole. If a 20 solar mass black hole somehow entered our solar system, the consequences would be catastrophic, but not immediate. Black holes don't reach out and grab things. They obey the same laws of orbital mechanics as any other massive object. If the Sun were suddenly replaced by a 20 solar mass black hole, Earth's orbit wouldn't change. We'd continue orbiting at the same distance, with the same period. We'd freeze because the Sun's light would be gone, but we wouldn't fall into the black hole. But if this black hole passed through the solar system on a trajectory that didn't come too close to any planets, it might perturb orbits but cause no direct destruction. As it approached from interstellar space, its gravity would begin affecting the outer planets. Neptune and Uranus, the outermost planets, would experience orbital perturbations. their orbits might become more elliptical or shift slightly. If the black hole passed within a few astronomical units, if it came within the orbital distance of Jupiter, things would get much worse. Jupiter and Saturn, the gas giants, would experience strong gravitational interactions. The three-body problem, the interaction between the black hole, the sun, and a planet, leads to chaotic dynamics. Small differences in initial conditions lead to vastly different outcomes. Some simulations might show Jupiter ejected from the solar system entirely, flung out into interstellar space by the gravitational slingshot effect. Others might show Jupiter's orbit becoming highly elliptical, taking it much closer to or farther from the Sun than its current nearly circular path. Closer still, and Earth would be in danger. Not from falling into the black hole directly. That's actually unlikely given the vast distances and small size of the black hole, but from having our orbit radically altered. Gravitational interactions could throw Earth into an eccentric orbit that takes us too close to the Sun during perihelia, the closest point, or too far during aphelia, the farthest point. Either way, the climate would be catastrophically disrupted. If we passed too close to the Sun, surface temperatures would spike, oceans would boil, the atmosphere would be stripped away, Earth would become Venus-like, a hellish oven. If we were flung too far, we'd enter a permanent ice age. The sun would appear smaller and dimmer, temperatures would plummet, oceans would freeze solid. The atmosphere might freeze out, snowing onto the surface as solid nitrogen and oxygen. In the very worst case, a close pass might tidally disrupt Earth if the black hole came within about 100,000 kilometers, close enough that different parts of Earth experience significantly different gravitational pulls. Our planet could be torn apart. The side facing the black hole would be pulled harder than the center, which would be pulled harder than the far side. If this difference exceeded Earth's structural strength, the solid Earth would fracture. Imagine the Rocky Mountains pulled away from the continent, not by tectonic forces, but by differential gravity. Imagine the oceans lifted from their basins, massive tsunamis, kilometers high, sweeping across continents, except the continents themselves are breaking apart. Earthquakes of unimaginable magnitude as tectonic plates shatter. Volcanic eruptions as the mantle depressurizes. The atmosphere, no longer held by a coherent planet, boiling into space. Within hours or days, Earth would be transformed from a living world into a debris field, a cloud of rock and metal and water vapor spreading along Earth's orbital path. Some material would be captured by the black hole, forming a temporary accretion disk. This disk would heat up and glow, emitting X-rays and visible light, a brief monument to a world that no longer exists. The rest of the debris would scatter, some falling into the sun, some ejected from the solar system, some settling into new orbits, where it might eventually coalesce into asteroids, or perhaps, over millions of years, a new rocky body. This is not something you need to worry about. The nearest known stellar mass black hole is over 1,000 light-years away, and it's not moving toward us. The galaxy is vast, and stellar mass black holes are rare. There are perhaps 100 million stellar mass black holes in the Milky Way, which sounds like a lot until you realize the galaxy contains several hundred billion stars and is 100,000 light-years across. The odds of one passing through our solar system in the remaining lifetime of the Sun, about 5 billion years, are essentially zero, far smaller than the odds of the Sun being struck by a rogue star, which is also vanishingly unlikely. But the thought experiment is valuable because it illustrates an important point. Black holes don't destroy through some mystical power. They destroy through gravity, the same force that holds you in your chair right now, the same force that keeps the moon orbiting Earth and Earth orbiting the sun. It's just gravity amplified to an extreme that makes planetary forces look trivial. And understanding this helps us appreciate what happens when we encounter even larger black holes. Now we need to make a leap. Not a small step in mass, but a jump of factors of thousands or even millions. We need to cross the mass gap and enter the realm of supermassive black holes, the monsters that lurk at the hearts of galaxies. This gap is one of the great puzzles of astrophysics. We've found stellar mass black holes up to about 100 solar masses. we found supermassive black holes starting at about 100,000 solar masses. But in between, there's a curious absence. Intermediate mass black holes, if they exist, are rare and hard to detect. Recently, astronomers have found a few candidates. LIGO and Virgo gravitational wave detectors have found black holes in the intermediate range, around 100 to a few hundred solar masses, formed from the mergers of stellar mass black holes. Some globular clusters, dense spheres of old stars orbiting in galactic halos, show evidence of intermediate mass black holes at their centers, with masses of a few thousand solar masses. But these are exceptions, rare finds in decades of searching. This gap tells us something about how supermassive black holes form. They can't simply be the remnants of massive stars, because no star is massive enough to leave behind a million solar mass black hole when it dies. The most massive stars, up to perhaps 200 solar masses, leave behind black holes of at most 100 solar masses. To get to millions or billions of solar masses, supermassive black holes must grow through other mechanisms. Mergers are one possibility. Many stellar mass black holes colliding and combining over millions of years. In dense stellar environments, like galactic centers or nuclear star clusters, black holes can sink to the center through dynamical friction, a process where they gravitationally interact with surrounding stars and gradually lose energy and spiral inward. Once multiple black holes reach the center, they can merge, doubling the mass with each merger. But mergers alone might not be fast enough. Direct collapse of massive gas clouds in the early universe is another possibility. If conditions are right, if a cloud of gas can remain cool enough to avoid fragmenting into stars but massive enough to overcome internal pressure, it could collapse directly into a large black hole, perhaps 100,000 solar masses, without ever forming a star. These would be seeds, starting points that then grow through accretion. Continuous accretion over billions of years is the third mechanism. Black holes at galactic centers have access to large amounts of gas. Galaxies merge, bringing fresh gas supplies. Gas clouds fall inward. Stars pass close and are disrupted, their material feeding the black hole. Over cosmic time, a black hole can grow significantly through steady feeding. We don't fully understand which mechanism is most important, and the fact that we've found supermassive black holes in galaxies less than 1 billion years old makes the puzzle even more perplexing. These black holes appeared too early, grew too fast. There shouldn't have been enough time for them to accumulate so much mass through conventional mechanisms. The universe at that time was less than 10% of its current age. Either we're missing something about how they grow, or some of them formed through processes that don't operate in the modern universe, like direct collapse in the unique conditions of the very early cosmos. Let's start our exploration of supermassive black holes with a relatively modest example. 1 million solar masses. The event horizon radius for such a black hole is about 3 million kilometers, about 2 million miles. That's about 4 times the radius of the Sun. Imagine a spherical region of darkness, 4 solar radii across, a hole in space big enough to swallow the Sun with room left over. Mercury, the closest planet to the Sun, orbits at an average distance of about 58 million kilometers. This black hole's event horizon is about 3 million kilometers in radius, so 6 million kilometers in diameter. Mercury could fit inside this black hole's orbit, though it would orbit the black hole, not be inside the event horizon. The event horizon itself, the point of no return, is much smaller than Mercury's orbital distance. This black hole is smaller than the inner solar system, but it contains 1 million times the Sun's mass. The black hole at the center of our galaxy, Sagittarius A star, is about 4.3 million solar masses. Its event horizon is about 12 million kilometers in radius, which corresponds to a diameter of about 24 million kilometers. Light takes about 40 seconds to cross this distance, so we say the event horizon has a radius of about 20 light seconds. To put this in perspective, the Sun is about 8 light minutes from Earth, which is about 500 light seconds. Sagittarius A star's event horizon is about 4% of the distance from Earth to the Sun. It's tiny compared to astronomical distances, yet it contains more mass than 4 million suns. Sagittarius A star sits at the galactic center, about 26,000 light-years from Earth. It's invisible in visible light, hidden behind clouds of dust that obscure our view of the inner galaxy. We can't see through to the galactic center in optical wavelengths, but we can detect Sagittarius A star through radio emissions and by watching the orbits of stars nearby. These stars, particularly a group called the S stars, orbit very close to Sagittarius A star with very short periods. One star, called S2, completes an orbit every 16 years. At its closest approach, it comes within about 17 light-hours of the black hole, about 1,000 times the event horizon radius. It's traveling at about 5,000 kilometers per second, about 2.5% of the speed of light. At that speed, you could travel from Earth to the Moon in less than a minute. By tracking S2's orbit with exquisite precision, using adaptive optics systems that correct for atmospheric distortion in real time, astronomers have measured the mass of Sagittarius A star to high accuracy. They've also seen relativistic effects in S2's orbit. The orbit isn't a perfect ellipse. General relativity predicts the orbit should process, rotating slowly over time, with the point of closest approach shifting slightly with each orbit. This is the same effect that was observed in Mercury's orbit around the Sun, one of the first confirmations of general relativity. But for S2 orbiting Sagittarius A star, the effect is much larger, about 12 arc-minutes per orbit, compared to Mercury's 43 arc-seconds per century. We've measured this precession. It matches Einstein's predictions to within the measurement uncertainties. Every orbit of S2 is another confirmation that general relativity is correct, that space-time really is curved by mass, that gravity really is geometry. Astronomers have also detected gravitational redshift in light from S2. When the star is at its closest approach to the black hole, deep in the gravitational field, the light emitted from the star is redshifted, stretched to longer wavelengths. This effect is small, a change of about 200 parts per million in wavelength, but it's measurable with modern spectrographs. The light is literally climbing out of the gravitational well, losing energy in the process, and that energy loss appears as a shift to longer wavelengths. To track S2 with the precision needed to measure these effects requires extraordinary technology. The Keck Observatory and the Very Large Telescope use adaptive optics, systems that measure atmospheric turbulence and deform a flexible mirror hundreds of times per second to compensate. Without adaptive optics, atmospheric turbulence blurs the image, and you can't resolve individual stars near the galactic center. With adaptive optics, you achieve resolution almost as good as if the telescope were in space. The observations span decades. Astronomers have been tracking CES-2 since the 1990s. Each observation adds another point to the orbit. Over time, the ellipse becomes clear. The precession becomes measurable. The gravitational redshift becomes detectable. It's a triumph of observational astronomy and a powerful test of general relativity in a regime where Newtonian gravity fails completely. In May of 2022, the Event Horizon Telescope collaboration released an image of Sagittarius A star. Like their earlier image of M87 star, it shows a glowing ring around a dark center. The ring is light from gas orbiting just outside the event horizon. Some of this light is bent around the back of the black hole by gravitational lensing, creating a photon ring, a halo of multiply-imaged light that encircles the shadow. The shadow itself is about 2.5 times the diameter of the event horizon. This enlargement is due to gravitational lensing and the behavior of light near the black hole. Photons that pass close to the black hole are bent inward by the curved spacetime. The closer they pass, the more they're bent. There's a critical distance called the photon sphere, where photons can orbit the black hole in unstable circular orbits. Light emitted inward of this radius falls into the black hole. Light emitted outward escapes. The boundary creates the edge of the shadow we see. For a black hole of Sagittarius A star's mass, something interesting happens to the tidal forces. They become weaker at the event horizon. Not weaker in an absolute sense. Gravity at the horizon is still strong enough to trap light, but weaker in terms of the gradient, the rate of change of gravity with distance. For a stellar mass black hole, Tidal forces at the event horizon are immense because the horizon is small. The difference in gravity between a point just outside the horizon and a point a meter closer is enormous. The gravitational acceleration changes by huge amounts over short distances. But for a supermassive black hole, the event horizon is large. The gravitational field is strong enough that escape velocity equals the speed of light, but it's strong over a larger region, so the gradient is gentler. The rate of change of gravity with distance is smaller. The difference in gravity between your head and feet at the event horizon of Sagittarius A star would be noticeable, like a strong pull on your feet, but not immediately lethal. You could, in principle, survive crossing the event horizon of a supermassive black hole. You'd fall through, feeling moderate discomfort from tidal forces, perhaps like being stretched on a rack, but not being torn apart. For a few seconds, or even a few minutes, depending on the exact mass, you'd be inside the black hole, falling toward the singularity, but still intact, still alive, still capable of thought. This is both fascinating and terrifying. Fascinating because it means the interior of a black hole is briefly a place where a human could exist. You could look around, take measurements, experience what it's like to be inside an event horizon. Terrifying because you'd know with absolute certainty that you're doomed. Every direction you look leads to the singularity. Every path through space-time terminates there. You can't escape. You can't even slow down. You're falling through time itself toward an end that you can see approaching but cannot avoid. Inside the event horizon, the singularity is not a place in space. It's a moment in time. It's in your future, as inevitable as tomorrow. Just as you cannot avoid tomorrow by moving left or right, you cannot avoid the singularity by changing your direction in space. All directions in space are equivalent inside the horizon. They all lead to the same moment, the singularity. As you fall, tidal forces would gradually increase. Closer to the singularity, the gradient of gravity becomes steeper. The difference in gravitational pull between your head and feet grows. Eventually, perhaps minutes after crossing the horizon for a black hole of Sagittarius A star's size, the tidal forces would become lethal. You'd be stretched and compressed, squeezed along some directions and pulled along others, torn apart by forces that grow without limit as you approach the singularity. From your perspective, the journey is finite. You cross the horizon, you fall for a while, and then you reach the singularity, and your story ends. The time from horizon to singularity for a non-rotating black hole is about 15 microseconds times the black hole's mass in solar masses. For Sagittarius A star, that's about 65 seconds. 1 minute and 5 seconds from horizon crossing to the singularity. Though in practice, you'd probably be killed by tidal forces before reaching the singularity itself. From the perspective of someone outside, watching you fall in, something very different happens. They see you approach the horizon, slow down, redshift and fade. They never see you cross. Time dilation means that your moment of crossing is infinitely far in their future. If they could watch for 1 trillion years, they'd see you frozen just outside the horizon, dimmed to invisibility, but never quite crossing. If you could somehow look back as you fell, you'd see the universe outside the black hole speeding up. Time dilation works both ways. As time slows down for you relative to the outside world speeds up relative to you. You'd watch stars being born and dying in fast forward. You'd see the galaxy evolve. If you fell into Sagittarius A star and looked back, you'd see the Milky Way's remaining history play out before your eyes in the minute before you reach the singularity. You'd watch our solar system. You'd see the sun exhaust its hydrogen and expand into a red giant, engulfing the inner planets. You'd see it shed its outer layers, creating a planetary nebula. You'd see it fade to a white dwarf. All of this, which will take billions of years from Earth's perspective, would happen in seconds from yours. You'd watch the future unfold while falling toward your own personal end of time. This is one of the strangest implications of general relativity. The future isn't fixed. It depends on your reference frame. From outside the black hole, your future is to freeze at the horizon. From your perspective, your future is to cross the horizon and reach the singularity. Both futures are real. Both happen. They're just different descriptions of the same space-time geometry, viewed from different vantage points. Let's jump up in mass by more than a factor of 1,000. 100 million solar mass black hole has an event horizon radius of about 300 million kilometers, roughly 2 astronomical units. An astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. This black hole's event horizon extends to twice Earth's orbital distance. It's larger than the orbit of Venus and nearly as large as Earth's orbit around the Sun. The entire inner solar system could fit inside this black hole's event horizon. Mercury, Venus, Earth, Mars, all the way out to the asteroid belt, all of it could be swallowed by this monster. And this is still considered a relatively small supermassive black hole. There are much larger ones. The black hole at the center of the galaxy, M87, the one in the first Event Horizon Telescope image from 2019, is about 6.5 billion solar masses. Its event horizon has a radius of about 12 billion kilometers, about 80 AU. To put that in perspective, Neptune orbits the Sun at 30 AU, Pluto's orbit ranges from 30 to 50 AU. The entire region of our Sun's planets would fit comfortably inside M87 Finest Star's event horizon with room left over. M87 Star is extraordinary, not just for its mass, but for what it does. It powers a relativistic jet, a beam of matter and energy that extends over 5,000 light-years from the galaxy's core. This jet is visible in radio wavelengths and with the Hubble Space Telescope, even in optical light. It's a consequence of the black hole's rotation and the magnetic fields in the accretion disk. Here's how it works, in simplified terms. The black hole is spinning, rotating on its axis at a substantial fraction of the maximum possible rate. This rotation drags space-time around with it, creating a region called the ergosphere, where space-time itself is rotating. The ergosphere exists outside the event horizon. Inside the ergosphere, you cannot stand still. You must move in the direction of rotation. Space-time itself is being dragged along like water in a whirlpool, and you're caught in the current. The accretion disk around the black hole contains ionized gas, which means it's threaded with magnetic fields. Magnetic field lines are anchored in the charged particles of the gas. These fields are anchored in the disk but extend outward and inward. Some field lines pass through the ergosphere and connect to the black hole's horizon. The rotation of the black hole twists these field lines, coiling them up like a spring being wound. This twisting creates powerful electromagnetic forces. Matter in the accretion disk, mostly electrons and protons, gets accelerated along these twisted field lines. It's funneled toward the poles of the black hole, perpendicular to the disk, and ejected in narrow jets. The particles are accelerated to speeds exceeding 99.99% of the speed of light. They carry enormous amounts of energy, extracted ultimately from the black hole's rotational energy. These jets can extend for millions of light-years. They plow through intergalactic space, creating giant lobes of radio emission where the jet material finally slows down and spreads out. M87's jet is visible for over 5,000 light-years, but the total structure, including the lobes, extends much farther. Radio telescopes see emission from regions larger than M87's host galaxy. The jet has structure. There's a central spine where the flow is fastest and most collimated. Surrounding it is a sheath, where the flow is slower and more turbulent. The jet is not smooth. It has knots, bright regions where the emission is enhanced. These knots are thought to be shocks, places where faster-moving material catches up to slower-moving material and compresses it, heating it and causing enhanced emission. In 1999, astronomers observed a knot of emission in M87's jet that appeared to move at 6 times the speed of light. This wasn't a violation of relativity. It was a consequence of it. The phenomenon is called superluminal motion, and it occurs when matter moves toward you at close to light speed. Imagine a blob of plasma moving toward you at 99.5% of the speed of light. It emits light at 2 different times, separated by 1 year. The light from the first emission travels toward you. A year later, the blob emits again, but in that year, the blob has moved closer to you, almost catching up to the light it emitted earlier. So the light from the second emission takes much less than a year to reach you. You see the two emissions separated by much less than a year, making it appear that the blob moved much faster than light speed. The mathematics is straightforward. If something moves toward you at velocity close to the speed of light, its apparent transverse velocity, the speed it appears to move across the sky, can exceed the speed of light. The record is something like 40 times the speed of light for certain quasars. It's an illusion caused by geometry and light travel time, but it's a beautiful consequence of relativity. Quasars are extreme examples of active galactic nuclei. A quasar is a galaxy with an actively feeding supermassive black hole at its center. The black hole is consuming matter so rapidly that the accretion disk glows with the light of trillions of stars. Quasars are the most luminous, persistent objects in the universe. The brightest quasars have luminosities of 100 trillion times the Sun's luminosity, roughly 100,000 times more luminous than the entire Milky Way galaxy. To power this, the black hole must be consuming enormous amounts of matter. The most luminous quasars are accreting several hundred solar masses per year. That's comparable to the mass of the Sun every few days. The gas spirals inward, heats up, and radiates before crossing the event horizon. The 10% efficiency of black hole accretion means that if the quasar is accreting 100 solar masses per year, it's converting 10 solar masses per year into radiant energy. That's the energy equivalent of 10 suns completely annihilated, converted to pure energy every single year. Most quasars are very distant, which means we're seeing them as they were billions of years ago, when the universe was younger. The universe was denser then, richer in gas. Galaxies were colliding more frequently. Gas was more available to feed black holes. Black holes could grow more easily. In the early universe, quasars were common. In the modern universe, they're rare. Most supermassive black holes are quiescent now, sleeping giants that consume only occasional snacks of gas or tidally disrupted stars. Our Milky Way's black hole, Sagittarius A star, is dormant. It's not actively feeding. There's no dense accretion disk, no powerful jets. It emits some radiation, mostly in radio wavelengths from hot gas in its vicinity, but nothing compared to a quasar. If Sagittarius A star were feeding actively, if it were consuming matter at rates comparable to quasars, it would outshine every star in the galaxy. The galactic center would be a blazing beacon visible across billions of light years. But it's not, and that's good for us. An active quasar at the galactic center would bathe the galaxy in high-energy radiation. Life on Earth would be exposed to increased cosmic rays, X-rays, gamma rays. The effects would depend on the intensity and duration. At minimum, increased mutation rates, damage to DNA, higher cancer rates. At worst, mass extinction events, sterilization of the galactic habitable zone. Quasar activity is self-limiting. As the black hole feeds, the radiation from its accretion disk heats the surrounding gas. This heat provides pressure that opposes the infall of more gas. Eventually, the radiation pressure becomes strong enough to blow away the infalling gas, shutting off the black hole's food supply. This is called AGN feedback, active galactic nucleus feedback. It's thought to be the main mechanism that regulates black hole growth and also regulates star formation in massive galaxies. When a galaxy merges with another galaxy, the merger funnels gas toward the center. The black holes grow. Star formation increases. But the growing black holes eventually ignite as quasars. Their radiation heats the gas, drives winds and outflows, and shuts down both further black hole growth and star formation. The galaxy transitions from an actively star-forming blue galaxy to a passive red galaxy filled with old stars but forming few new ones. This transition is observed, and AGN feedback is the leading explanation. If M87 star replaced the Sun at the center of our solar system, the consequences would be immediate and absolute. The event horizon alone extends to about 80 AU, well past Neptune's orbit at 30 AU and past Pluto's orbit at 30 to 50 AU. Earth, along with all the inner planets, would be inside the event horizon from the moment of replacement. But here's something subtle that's worth understanding. Being inside the event horizon doesn't mean you immediately fall to the singularity. You'd still be in orbit, at least initially. The black hole's gravity, at Earth's location, 1 AU from the center, wouldn't necessarily be stronger than the Sun's was, depending on how the mass is distributed. Wait, that seems wrong. The black hole has 6.5 billion solar masses, much more than the Sun's 1 solar mass. Shouldn't gravity be stronger? Not necessarily. Gravity depends not just on the total mass, but on the distribution of mass. The Sun's mass is spread over a region about 700,000 kilometers in radius. Earth orbits at 150 million kilometers, well outside the Sun's surface. The gravitational force at Earth's location depends on the mass enclosed within Earth's orbit. If you compress the Sun to a black hole, its mass wouldn't change. If you were orbiting at Earth's distance before the compression, and you remain at Earth's distance after, the gravitational force you experience would be the same. Gravity at a given distance depends only on the mass within that distance, not on what's farther out, not on the density, just on the total mass enclosed. But M87 star has billions of times the Sun's mass. At 1 AU from its center, the gravitational force would be billions of times stronger than what Earth currently experiences. Earth's orbital velocity around the Sun is about 30 kilometers per second. To remain in a stable orbit at 1 AU around M87 star would require an orbital velocity of about 30,000 kilometers per second, 10% of the speed of light. Earth isn't moving that fast. Earth would fall inward. But even so, the fall wouldn't be instantaneous. Orbital mechanics inside a black hole are strange because the singularity is not just a place, but also a moment in time. Still, you could temporarily orbit inside the event horizon if your velocity were high enough. Photons orbit the black hole at the photon sphere, which is outside the horizon for a non-rotating black hole. But inside a rotating black hole, the geometry is more complex, and there are regions inside the event horizon where you could temporarily maintain a circular path before inevitably falling to the singularity. What's changed is not the local gravity in an absolute sense, but the global structure of space-time. Inside the event horizon, all paths lead eventually to the singularity. But eventually could be days or even weeks, depending on your specific trajectory and the black hole's mass. You'd be inside the black hole, falling inexorably toward the center. But with time remaining, the Sun would be gone, replaced by darkness. Earth would receive no sunlight. Temperatures would plummet. The surface temperature of Earth is maintained by a balance between absorbed sunlight and emitted infrared radiation. Remove the sunlight, and the temperature drops rapidly. Within days, the surface would freeze. Oceans would begin turning to ice. The atmosphere would begin snowing out. Carbon dioxide first, then oxygen and nitrogen at lower temperatures. Humanity would have to retreat into shelters with artificial heat sources, nuclear reactors, geothermal plants, anything that doesn't depend on sunlight. We could survive for weeks or months, perhaps longer, if we'd prepared, but all the while, we'd be falling. Earth's orbit would decay, not because of friction or radiation, but because space-time geometry itself funnels all trajectories toward the singularity. You'd have time to understand what was happening, time to say goodbye, time to contemplate the end, and then, inevitably, tidal forces would grow. At first imperceptibly, then noticeably, then alarmingly. Earth would feel stress, the planet being stretched slightly in one direction and compressed in others. Earthquakes would increase in frequency and magnitude. Volcanic eruptions as the mantle adjusted to the changing stress. The crust fracturing as the planet deformed beyond what its material strength could withstand. Eventually, Earth would be torn apart, shredded into a stream of debris that spirals inward, heating up through compression and friction, glowing briefly before crossing the final threshold and disappearing into the singularity. The entire story, from the moment M87 star replaced the Sun to Earth's final destruction, might take weeks. Weeks of darkness, cold, fear, and the growing realization that there's no escape, no last-minute rescue, no way out, just an inexorable fall into oblivion. At this scale, black holes begin to dominate their environments in profound ways. The sphere of influence, the region where the black hole's gravity is the dominant force, extends for hundreds or thousands of light-years around M87 star. Stars within this region orbit the black hole more strongly than they orbit the galaxy itself. Their motion is determined primarily by the black hole's gravity. Entire star clusters orbit M87 star. Globular clusters, spherical collections of hundreds of thousands of ancient stars, pass through the galactic center on orbits that take millions of years. Some are disrupted by the black hole's tidal forces. Stars on the side of the cluster closer to the black hole are pulled harder than stars farther away. Over time, this differential pull stretches the cluster, pulling stars away from its edges. Eventually, the cluster is destroyed, its stars scattered into orbits around the black hole or ejected from the galaxy entirely. The black hole shapes the evolution of its host galaxy. It's not just an object within the galaxy, it's an architect of galactic structure. The correlation between black hole mass and galaxy properties, like the velocity dispersion of stars in the galactic bulge, is one of the most surprising discoveries in modern astrophysics. The M-sigma relation, as it's called, shows that black hole mass is tightly correlated with the velocity dispersion of stars in the galactic bulge, the central region of the galaxy. Velocity dispersion is a measure of how fast stars are moving randomly, which is related to the mass and size of the bulge. The correlation is tight, with very little scatter. This is surprising because the black hole is tiny compared to the galaxy. M87 star, despite being 6.5 billion solar masses, contains only about 1/10% of the galaxy's total stellar mass. M87 is a giant elliptical galaxy with a total stellar mass of several trillion solar masses. The black hole is about 0.1% of that. Yet there's a tight relationship between the black hole's mass and the properties of stars thousands of light-years away. Somehow, the black hole and galaxy know about each other. They grow together, regulate each other, influence each other across distances that light takes millennia to cross. The leading explanation is coevolution through AGN feedback, the process where black hole activity regulates star formation and gas flows in the galaxy. Now let's go even larger. 618 is one of the most massive black holes known, with a mass estimated at 66 billion solar masses. Its event horizon diameter is about 390 billion kilometers, which translates to about 2600 AU, or 0.04 light-years. Light takes about 2 weeks to cross from one side of this event horizon to the other. This is an object so large that its size is measured in weeks of light travel time. The distance from the Sun to the nearest star, Proxima Centauri, is 4.2 light-years. TUN 618's event horizon is about 1% of that distance. Still far smaller than interstellar distances, but approaching the scale where cosmic distances start to become relevant. TUN 618 was discovered in the 1970s during a photographic survey of the sky. It appeared as a faint blue point of light, unremarkable except for its unusual spectral properties. Further observations revealed it was extraordinarily distant, about 10.4 billion light-years away. The light we see from TOT 618 left when the universe was only about 3 billion years old, less than a quarter of its current age. Measuring the mass of such a distant object is challenging. Astronomers use several methods. One is reverberation mapping, which measures the time delay between changes in the accretion disk's luminosity and changes in emission from surrounding gas clouds. This time delay tells you the size of the region, and from the size and the gas velocity, you can calculate the mass. Another method uses the luminosity and assumes the black hole is radiating at some fraction of the Eddington limit. Neither method is perfect, and mass estimates for extremely distant quasars have large uncertainties. Early estimates placed TUN 618 at around 66 billion solar masses, making it one of the most massive black holes known. More recent observations and refined techniques have adjusted this somewhat, but it remains in the range of several tens of billions of solar masses. It's definitely among the most extreme objects in the universe. At that epoch, when the universe was only about 3 billion years old, TON 618 was already tens of billions of solar masses. It had somehow grown to this stupendous size in the relatively short time since the Big Bang. The universe began 13.8 billion years ago. The first stars formed around 100 to 200 million years after the Big Bang. That leaves about 2.7 billion years for TON 618 to grow from whatever seed it started with to its observed mass. If TON 618 started as a stellar mass black hole of 100 solar masses formed from the first generation of stars, and if it grew at the maximum Eddington limited rate, doubling its mass every 50 million years or so, it would need about 800 million years to reach 66 billion solar masses. That's well within the available time, but it's tight, and it requires continuous accretion at nearly the maximum possible rate for hundreds of millions of years. If TON 618 started even more massive, perhaps from direct collapse of a massive gas cloud into a 100,000 solar mass seed, the timeline becomes more comfortable. Starting from 100,000 solar masses and growing at the Eddington limit, you could reach 66 billion solar masses in about 600 million years. Again, within the available time, but requiring optimal conditions. The problem is that sustained Eddington limited growth is difficult. As the black hole feeds, it heats the surrounding gas, which creates pressure that opposes further infall. The black hole alternates between feeding and fasting, growing in spurts rather than continuously. If the average growth rate is lower than the Eddington limit, the timeline becomes problematic. TON 618 might have needed super Eddington accretion, feeding faster than standard models allow, or it might have experienced numerous mergers that added mass quickly. TON 618 is not just massive, it's also incredibly luminous. Its bolometric luminosity, the total energy output across all wavelengths, is about 140 trillion times the Sun's luminosity. That's about 40,000 times more luminous than the entire Milky Way galaxy. A single black hole, accreting matter at a prodigious rate, outshining entire galaxies containing hundreds of billions of stars. To power this luminosity, assuming 10% efficiency for converting mass to energy, TOT 618 must be consuming about 600 Earth masses of material every hour. That's about 20 solar masses per day. At this rate, it would consume the equivalent of our entire Sun, all one solar mass, in about 3 weeks. It's eating stars faster than most stars form in galaxies. This level of consumption can't continue indefinitely. There's a limit to how fast a black hole can grow through accretion, the Eddington limit. As matter falls toward a black hole and heats up, it emits radiation. This radiation exerts outward pressure on surrounding matter through radiation pressure, the momentum carried by photons. If the radiation pressure becomes too strong, it blows away the infalling material, choking off the black hole's food supply. The Eddington limit depends on the black hole's mass. More massive black holes have more gravity, which can overcome stronger radiation pressure, so they can accrete faster in absolute terms. But the limit, in terms of the rate of mass growth, is proportional to the black hole's current mass. A black hole can grow at most exponentially with time at the Eddington limit, doubling its mass every Eddington time, which is about 50 million years for efficient accretion. TON 618 is radiating at close to or possibly exceeding the Eddington limit. If it's radiating at the Eddington limit, it's accreting as fast as radiation pressure allows. If it's radiating above the Eddington limit, it's somehow exceeding this theoretical maximum, possibly through geometries or mechanisms that circumvent the usual radiation pressure constraints, like thick accretion disks where radiation is trapped and advected inward rather than escaping outward. The fact that quasars, like TON 618, shine so brightly suggests either that they're very close to the Eddington limit, extracting energy from accretion as efficiently as possible, or that they're exceeding it through processes we don't fully understand. Inside a black hole this massive, you could survive for hours or even days. the tidal forces at the event horizon would be incredibly weak. For T 618, the tidal acceleration at the event horizon, the difference in gravitational acceleration over a human body's height, would be less than 1/1,000,000th of Earth's surface gravity. You wouldn't feel it at all. You'd cross the horizon without noticing. You'd look around, see nothing unusual in your immediate vicinity, and only gradually realize that something was wrong. There's no marker at the event horizon, no sign saying point of no return. It's just a mathematical surface in space-time. You'd need sophisticated instruments to detect that you'd crossed it. Or you'd realize it later, when you tried to turn back or send a signal outward, and discovered that no amount of acceleration could prevent you from falling deeper inward. You might orbit inside the black hole for a while, falling in a spiral trajectory toward the singularity. If you'd crossed the horizon with significant angular momentum, you could orbit for hours or even days before the orbit decayed and you fell to the singularity. You'd have time to explore, time to take measurements if you had instruments, time to think about what's happening, but eventually you'd notice the tidal forces growing. Slowly at first, imperceptibly, then measurably. You might notice that you felt slightly stretched, a gentle pull along your body's length. Hours into your fall, the sensation would intensify. Your body would start to elongate. The discomfort would turn to pain. Your skeleton would feel the stress. Your organs would be pulled slightly out of position. In the final hour before reaching the singularity, the tidal forces would become dangerous. Your body would elongate noticeably. Your bones would separate. Your circulatory system would struggle to pump blood through an increasingly stretched body. Your nervous system would be compromised as neurons were pulled apart. In the final minutes, you'd be torn apart, reduced to a stream of tissue, then cells, then molecules, then atoms. In the final microseconds, even atomic nuclei might be disrupted. Protons and neutrons separated by forces that overcome the strong nuclear force, and then you'd reach the singularity, whatever that truly is, and your story would end. What happens at the singularity is the greatest unsolved problem in gravitational physics. General relativity predicts that space-time curvature becomes infinite, that density becomes infinite, that the laws of physics as we know them simply stop applying. Infinite values in a physical theory usually indicate that the theory has reached its limits. They're not descriptions of reality. They're admissions that we don't know what happens next. Quantum mechanics must play a role at the singularity. When distances become as small as the Planck length, about 10 to the minus 35 meters, quantum effects dominate, but we don't have a quantum theory of gravity. String theory, loop quantum gravity, and other approaches suggest that the singularity might be replaced by something else, a region of Planck-scale physics, a bounce that connects to another region of space-time, or perhaps something we haven't even imagined yet. One possibility is a Planck star. In loop quantum gravity, space-time is made of discrete units, tiny loops connected in a network. As you approach the singularity, you'd encounter these quantum structures. The crushing force of gravity would be opposed by quantum pressure, an effect arising from the discrete nature of space-time at the Planck scale. Instead of infinite density, you'd reach a maximum density, the Planck density, about 10 to the 96 kilograms per cubic meter. At that density, you'd have about 10 to the 54 solar masses in a volume the size of a proton. At the Planck density, quantum effects halt the collapse. The matter bounces, rebounding from the quantum floor. But this bounce happens inside the event horizon, in a region that's causally disconnected from the outside universe. The bounce can't send signals outward. From the outside, the black hole appears unchanged. But inside, where we can't see, the singularity might not exist. Instead, there's a transition, a bounce, perhaps the seed of a new expanding universe. This is speculative, and we may never know if it's correct. The singularity might be forever beyond our reach, hidden behind the event horizon where no information can escape. It might be the one place in the universe that's permanently unknowable, where even in principle, no measurement or observation could tell us what's there. There's a principle in physics called cosmic censorship, proposed by Roger Penrose in the 1960s. It states that singularities are always hidden behind event horizons. Nature doesn't allow naked singularities, places where space-time curvature becomes infinite but can be seen from the outside. If this principle is true, and it seems to be based on all cases we've studied, then the universe has a kind of modesty. It hides its breakdowns from view, concealing them behind horizons where no information can escape. We're protected from seeing infinities. The universe keeps its embarrassing failures of physics out of sight. Some solutions to Einstein's equations do allow naked singularities, mathematical solutions where the singularity is visible. But these solutions require special conditions, and it's suspected that they're unstable, that any small perturbation would cause them to form event horizons and hide the singularity. Whether cosmic censorship is a fundamental law or just an empirical observation is an open question, one of the deepest in gravitational physics. Now we're going to push to the very edge of what the universe allows. The largest black holes ever discovered are in the realm of 100 billion solar masses. Phoenix A, located at the center of the Phoenix galaxy cluster, about 5.7 billion light-years from Earth, is currently the most massive black hole confirmed, at roughly 100 billion solar masses. The event horizon radius of Phoenix A is about 600 billion kilometers, or about 4,000 AU, that's 0.06 light-years. In the time it takes light to cross from one side of this black hole to the other, about a month and a half passes on Earth. This is an object whose size is measured in light months. To put this in perspective, Voyager 1, humanity's most distant spacecraft, launched in 1977 and has been traveling outward through the solar system for nearly 50 years. It's currently about 160 AU from the Sun, farther than any other human-made object. If Phoenix A were at the Sun's location, Voyager 1 would still be inside the event horizon. Everything we've ever sent into space, every satellite, every probe, every spacecraft, all of it would be inside this black hole. The entirety of human space exploration, spanning decades and reaching the edge of the solar system, would fit comfortably within Phoenix A's event horizon, with room left over. The mass of Phoenix A is comparable to all the stars in the central bulge of the Milky Way combined. The Milky Way's bulge contains about 10 billion stars, mostly old red giants and smaller stars. Phoenix A alone contains about 10 times that mass. It's a significant fraction of the mass of an entire galaxy, compressed into a region that, while large, is still tiny compared to galactic scales. Phoenix A sits at the center of a massive galaxy within the Phoenix galaxy cluster. A galaxy cluster is a gravitationally bound collection of hundreds or thousands of galaxies, spanning millions of light-years. The Phoenix cluster is one of the most massive clusters known, containing thousands of galaxies with a total mass of several quadrillion solar masses, dominated by dark matter, but with a substantial component of stars and gas. The central galaxy, in a cluster, called the brightest cluster galaxy, or BCG, is typically an enormous elliptical galaxy formed from countless mergers over billions of years. BCGs are the most massive galaxies in the universe, containing trillions of stars, and at the center of many BCGs sits an ultra-massive black hole, the product of all those mergers. Each time two galaxies merge, their central black holes eventually sink to the center of the merged system through a process called dynamical friction. As a black hole moves through a sea of stars, it gravitationally interacts with them. Stars passing behind the black hole are accelerated, gaining energy. Stars passing in front are decelerated, losing energy. This asymmetry creates a drag force that slowly removes energy from the black hole's orbit, causing it to spiral inward. Once both black holes reach the galactic center, they orbit each other, gradually spiraling inward as they lose energy to gravitational wave emission. Eventually, they merge, combining their masses. If Phoenix A's host galaxy experienced hundreds or thousands of mergers over its history, each bringing a black hole of millions or billions of solar masses, the cumulative effect could build a black hole of 100 billion solar masses. The influence of Phoenix A extends for tens of thousands of light-years. Stars within this region orbit the black hole more strongly than they orbit the galaxy. Their velocities are determined primarily by the black hole's gravity. Entire globular clusters, dense balls of hundreds of thousands of old stars, orbit Phoenix A on paths that take millions of years to complete. What would it be like inside Phoenix A? The event horizon is so large, and the tidal forces at the horizon so weak, that you could cross without feeling anything unusual. The tidal acceleration at the event horizon of a 100 billion solar mass black hole is less than 1/10,000,000th of Earth's surface gravity. It's completely imperceptible. You'd be inside a black hole, falling toward the singularity, but your immediate experience would be eerily normal. Time to the singularity, assuming you fell straight in without orbiting, would be measured in days or possibly weeks. For a non-rotating black hole, the proper time from horizon to singularity is proportional to the black hole's mass. For Phoenix A, that's about 11 days. 11 days of falling through darkness toward an unknowable end. But if you had angular momentum, if you crossed the horizon on a trajectory that wasn't directly radial, you could orbit inside the black hole, extending your lifetime. The orbit wouldn't be stable, it would decay over time. But you might survive for weeks, spiraling slowly inward, feeling the tidal forces grow incrementally. This is a significant span of time. You could live a meaningful final chapter of your life, knowing that you can never escape, that everyone and everything you've ever known is irrevocably in your past, separated from you by a horizon you can never recross. You'd be the ultimate exile, cut off from the entire observable universe, with nothing ahead but the singularity. The interior would be dark. No light from outside can reach inward past the event horizon. Any light emitted inside is also trapped, falling toward the singularity just like matter. If you had a flashlight, you could see things near you, illuminated by your own light. But looking outward, toward where the event horizon lies, you'd see nothing. Absolute darkness in all directions except perhaps the direction toward the singularity, which might appear as some kind of structure in space-time. Though, what exactly you'd see is unclear, because we don't have a good description of the singularity's nature. You might encounter other infalling matter. Anything that crossed the horizon is falling toward the singularity along with you. Gas, dust, perhaps even other explorers, if some advanced civilization had decided to probe the black hole's interior. You'd all be doomed together, sharing the same inescapable fate, fellow travelers on a one-way journey to the end of space-time. Gradually, over your days inside, tidal forces would grow. They'd start barely perceptible, less than 1/1,000,000th of a G, and slowly amplify. You might not notice for the first several days. Eventually, perhaps a day before reaching the singularity, you'd begin to feel stretched. The sensation would be subtle at first, like a gentle pulling along your body's length. As you got closer, the pulling would intensify. By the time you were an hour from the singularity, the tidal forces would be comparable to Earth's gravity. You'd feel like you were hanging from a rope, your feet pulled downward, your head pulled upward, your spine would be stressed. It would be uncomfortable, perhaps painful, but not yet fatal. In the final minutes, the forces would exceed what your body could withstand. Your bones would separate, your tissues would tear, you'd be pulled apart. Not suddenly, but inexorably, stretched like taffy until you were no longer recognizable as human. In the final seconds, you'd be a stream of atoms. In the final microseconds, even atoms would be disrupted. This is perhaps more terrifying than instant spaghettification. With a stellar mass black hole, death is quick. You're torn apart in seconds, too fast to fully comprehend what's happening. But inside Phoenix A, you'd have days to anticipate. Days to watch the tidal forces slowly grow. Days to experience your body gradually deforming. And no matter what you did, no amount of willpower or technology could stop it. The geometry of space-time itself is pulling you apart. It's not a force you can resist with engines or shields. It's the structure of reality. Phoenix A is close to theoretical upper limits for black hole mass. For black hole mass, there are limits to how massive a black hole can become, set by the dynamics of galaxy formation and the finite amount of matter available to feed the black hole. Most of the mass in a galaxy is in stars, not gas. Stars move on orbits that don't intersect the black hole unless something perturbs their orbits. They're not going to fall in spontaneously. Gas can fall in more easily because collisions between gas clouds can remove angular momentum, allowing the gas to spiral inward. But even then, there are limits. As the black hole feeds, the radiation from its accretion disk heats the surrounding gas, driving it away. This is AGN feedback, and it's thought to be the main mechanism that stops black holes from growing indefinitely. The black hole feeds, becomes luminous, heats up its environment, blows away its food supply, and enters a quiescent phase. Black holes can also grow through mergers, which we'll discuss shortly. When two black holes merge, the result is a single black hole with nearly the combined mass of the two progenitors. Some mass energy is radiated away as gravitational waves, typically a few percent, but most of the mass is retained. Mergers can bypass the Eddington limit, doubling the black hole's mass instantly. If mergers are common, if galaxies collide frequently and their black holes merge, black holes can grow large quickly. In rich galaxy clusters, where galaxies are densely packed, mergers are more frequent. The central brightest cluster galaxy might experience hundreds of mergers over cosmic time, each bringing a black hole that eventually merges with the central black hole. But even with mergers, there are limits. The most massive galaxies contain about 1 trillion solar masses of stars and gas. If a black hole consumed 10% of its host galaxy's mass, which is far more than observed, it would reach 100 billion solar masses. Going beyond that would require either a very massive host galaxy, more massive than any we've observed, or some process that concentrates matter from multiple galaxies into a single black hole. Observationally, black holes much larger than 100 billion solar masses haven't been confirmed. Phoenix A is at the high end. There are a few other candidates with comparable masses, but none definitively larger. This might be because they don't exist, because there's a physical upper limit around this mass. Or it might be because they're rare, and we haven't looked hard enough, or because they're hard to detect, possibly because they're not actively feeding, and thus not luminous. Theoretically, you could imagine a black hole with 1 trillion solar masses, 10 times more massive than Phoenix A. Its event horizon would be about half a light year across. You could fit several stellar neighborhoods inside. At the nearest star to the Sun, Proxima Centauri, is 4.2 light-years away. This hypothetical black hole would be about 1/8 of that distance across. Its event horizon would be a region measured in light-years, approaching interstellar scales. But no black hole this massive has been observed, and it's not clear that galaxy dynamics would allow one to form. There might simply not have been enough time, even over the 13.8 billion years since the Big Bang, for a black hole to accumulate that much mass. As we look farther into the future, as galaxies continue to merge and black holes continue to grow, we might eventually see black holes reaching masses of 1 trillion solar masses or more. But in the current epoch, Phoenix A might be close to the maximum. When two supermassive black holes merge, the event is cataclysmic on a scale that's hard to fathom. In September of 2015, the LIGO observatories in the United States detected gravitational waves for the first time. The signal, designated GW150914, came from two stellar mass black holes, 29 and 36 solar masses, merging about 1.3 billion light-years away. The merger lasted a fraction of a second. As the black holes spiraled inward, they emitted gravitational waves that carried away orbital energy. The gravitational wave frequency and amplitude increased, creating a characteristic chirp signal. At the moment of merger, the two black holes combined into a single black hole of about 62 solar masses. 3 solar masses, about 5% of the total, were converted to energy and radiated away as gravitational waves. For 1/5 of a second, the merger released more power than all the stars in the observable universe combined. That's not a typo or an exaggeration. The peak luminosity of the merger, in gravitational wave power, exceeded 10 to the 49 watts. The Sun's luminosity is about 4 times 10 to the 26 watts. The Milky Way's total luminosity is about 10 to the 36 watts. The merger outshone 1 trillion galaxies. Of course, this power was in the form of gravitational waves, not electromagnetic radiation. Gravitational waves interact so weakly with matter that they pass through the Earth, through you, through everything, causing strains of about 1 part in 10 to the 21st, far too small to notice. But the sheer amount of energy involved, equivalent to 3 solar masses converted entirely to energy in a fraction of a second, is staggering. LIGO detected this by measuring changes in the lengths of 4-kilometer arms caused by passing gravitational waves. A gravitational wave is literally a ripple in the fabric of space-time, alternately stretching and squeezing space itself. As the wave passes, distances change. LIGO measures these changes using laser interferometry, bouncing light back and forth along perpendicular arms and looking for tiny differences in the light travel time. The sensitivity required is extraordinary. LIGO can detect length changes of about 10 to the minus 18 meters, about 1,000th the diameter of a proton. It's measuring movements smaller than an atomic nucleus. The fact that we can do this is a testament to human ingenuity. The mirrors are suspended on elaborate isolation systems to protect them from seismic vibrations. The laser light is amplified and recycled to increase sensitivity. The entire system is at the edge of what's technologically possible. Supermassive black hole mergers are even more extreme. When 2 billion solar mass black holes merge, they release energy equivalent to about 5% of their total mass, converted entirely into gravitational waves. That's about 100 million solar masses of energy, radiated away in minutes or hours. The gravitational wave luminosity, at the peak of such a merger, would be about 10 to the 59 watts, roughly 10 billion times more powerful than the stellar mass merger LIGO detected. For that brief time, the merging black holes would be the brightest thing in the universe, not in electromagnetic radiation, but in gravitational radiation. They'd be shaking space-time itself, creating waves that propagate across the cosmos at the speed of light. These waves carry information. By detecting them, we can learn about the masses of the merging black holes, their spins, their distance from us, even the shape of space-time near the event horizons. Future gravitational wave observatories, particularly space-based detectors like LISA, the Laser Interferometer Space Antenna, will be able to see supermassive black hole mergers across the entire observable universe. LISA is a planned mission, currently expected to launch in the 2030s. It will consist of 3 spacecraft flying in a triangular formation separated by 2.5 million kilometers. That's about 6 times the Earth-Moon distance. Laser beams will connect the spacecraft, forming a gravitational wave detector with arms millions of kilometers long. This enormous size makes LISA sensitive to lower-frequency gravitational waves, those with periods of minutes to hours, which are produced by supermassive black hole mergers. LIGO detects stellar mass black hole mergers, which produce gravitational waves at frequencies of tens to thousands of hertz, like audible sound. LIGO will detect supermassive black hole mergers, which produce gravitational waves at frequencies of millihertz, far below what LIGO can detect. The 2 observatories are complementary, covering different parts of the gravitational wave spectrum, just as optical telescopes and radio telescopes cover different parts of the electromagnetic spectrum. When LISA is operational, it will detect supermassive black hole mergers weekly. Every week, somewhere in the universe, 2 supermassive black holes will merge, and LISA will see it. We'll watch these titans collide and combine, measuring their properties, learning about the population of supermassive black holes throughout cosmic history. We'll test general relativity in the most extreme conditions the universe provides, checking whether Einstein's century-old theory still holds when space-time is twisted and warped to its limits. When the Milky Way and Andromeda galaxies merge, which will happen in about 4 billion years, the central black holes will eventually merge as well. Sagittarius A star, at 4 million solar masses, will combine with Andromeda's black hole, estimated at about 100 million solar masses. The result will be a black hole of about 104 million solar masses, give or take. The merger will generate gravitational waves, but by that time humanity, if it still exists, will be long gone or transformed into something unrecognizable. The merger process takes a long time. When the galaxies first collide, they pass through each other. Stars don't collide because they're so far apart, but the galaxy's shapes are distorted by tidal forces. Over hundreds of millions of years, the galaxies fall back together and merge, their stars mixing, their gas colliding and forming new stars. Eventually, the two central black holes sink to the center of the merged galaxy, but then they stall. They orbit each other at a separation of about a light-year, and the orbital decay slows dramatically. This is called the final parsec problem. The black holes have cleared out the stars in their vicinity through gravitational slingshot interactions. There aren't enough stars nearby to rob energy from the black hole's orbit, and at these separations, gravitational wave emission is very weak. The black holes might orbit each other for billions of years at this separation, unless something else intervenes. Possible mechanisms include a third black hole perturbing the orbit, a massive gas cloud that causes drag, or some other process that removes energy. Eventually, the black holes get close enough that gravitational wave emission becomes efficient. They spiral together rapidly in the final phase, merging in a cataclysmic event that shakes space-time. Gravitational waves pass through matter almost unimpeded. Unlike electromagnetic waves, which can be absorbed or scattered by intervening material, gravitational waves interact so weakly with matter that they travel through planets, stars, even black holes with almost no attenuation. This is why they're so hard to detect, but also why they're so valuable. They carry information from regions of space-time that are otherwise invisible to us, like the interiors of merging black holes in the moments before they combine. Could a supermassive black hole merger destroy nearby stars or planets? The gravitational waves themselves cause minimal direct damage. They stretch and squeeze space, but the amplitude is tiny even at the merger. A planet orbiting 1,000 light-years from a supermassive black hole merger might experience strains of 1 part in a million, causing tidal forces comparable to the Moon's effect on Earth. Uncomfortable for precision equipment, but not destructive to planets or stars. But the merger has other effects. The orbital dynamics disturb surrounding stars. Stars in orbits near the black holes can be flung out of the galaxy entirely, ejected at high velocities through gravitational slingshot effects. A planet orbiting one of those stars would be carried along, flung into intergalactic space, where it would drift forever in darkness, far from any other stars, with the galaxy receding behind it. Other stars might have their orbits radically altered, taking them on plunging paths through the galactic center, or out to the galactic halo. Planets in these systems would experience wild variations in temperature and radiation as their distance from the galactic center changed. Life on such planets would be disrupted, possibly sterilized by radiation or frozen by the loss of a stable stellar environment. The merger also releases electromagnetic radiation if there's gas around. The black hole's accretion disks might merge or be disrupted, creating flares of X-rays and visible light. If the black holes are feeding actively, the merger might trigger a burst of luminosity that temporarily increases the quasar's brightness by factors of 10 or more. Now we need to step back and think about what black holes mean, not just as astrophysical objects, but as windows into the nature of reality itself. Black holes force us to confront the deepest questions in physics. They're places where our two best theories, general relativity and quantum mechanics, both claim to apply but give contradictory answers. General relativity describes gravity as the curvature of space-time. It works beautifully for large objects and weak gravity. Quantum mechanics describes the behavior of particles at small scales. It works beautifully for atoms, nuclei, and fundamental particles. But at the singularity of a black hole, both theories should apply. The singularity is a point of infinite density, infinitely small, so quantum mechanics must be important. But it's also a region of infinite space-time curvature, so general relativity must apply. The problem is that general relativity and quantum mechanics are fundamentally incompatible in their current forms. They make different assumptions about the nature of space, time, and matter. General relativity treats space-time as a smooth continuum that can be curved and stretched. Quantum mechanics treats everything as discrete and probabilistic. General relativity is deterministic. Given initial conditions, you can predict the future exactly. Quantum mechanics is probabilistic. You can only predict the likelihood of different outcomes. At the singularity, these contradictions become unavoidable. We need a theory of quantum gravity, a theory that combines general relativity and quantum mechanics into a single framework. Many approaches have been tried: string theory, loop quantum gravity, causal sets, asymptotic safety, others. None have succeeded completely, though each has made progress. String theory proposes that fundamental particles aren't points, but tiny vibrating strings. The different vibrations correspond to different particles. Gravity arises from a particular vibration mode. String theory requires extra dimensions beyond the three of space and one of time we experience. These extra dimensions are thought to be compactified, curled up so small we don't notice them. In string theory, the singularity might be replaced by a string scale structure, something extended rather than point-like. The infinite density is avoided because there's a minimum size, the string length, below which the concept of distance becomes ill-defined. But string theory has many possible solutions, many possible ways the extra dimensions could be arranged, and we don't yet know which, if any, describes our universe. Loop quantum gravity takes a different approach. It starts from general relativity and tries to quantize space-time itself. Space-time becomes a network of discrete loops, a kind of quantum fabric. The smooth geometry of Einstein's theory emerges as an approximation when you zoom out. At the Planck scale, space-time is grainy, made of discrete units connected in a network. In loop quantum gravity, the singularity is replaced by a bounce. As matter collapses, it reaches the Planck density, about 10 to the 96 kilograms per cubic meter. At that density, quantum effects create a repulsive force, a kind of quantum pressure that halts the collapse. The matter bounces back. But this bounce happens inside the event horizon, causally disconnected from the outside. From the outside, the black hole appears unchanged, but inside, the singularity doesn't exist. These ideas are speculative. We have no experimental evidence for quantum gravity. We can't create Planck-scale conditions in laboratories. We can't observe the interiors of black holes. All we have are mathematical models, theoretical arguments, and the hope that one approach will eventually make predictions we can test. One prediction that's testable, at least in principle, comes from Hawking's discovery of black hole radiation. Hawking showed that black holes emit radiation due to quantum effects near the event horizon. This radiation has a temperature inversely proportional to the black hole's mass. For stellar mass black holes, the temperature is tiny, far colder than the cosmic microwave background. But the radiation exists. Over enormous timescales, this radiation carries away the black hole's mass. The black hole evaporates. The larger the black hole, the longer this takes. A solar mass black hole evaporates in about 10 to the 67 years. A supermassive black hole takes far longer, 10 to the 100 years or more. But eventually, even the largest black holes will evaporate, leaving nothing but radiation. Or will they? There's a puzzle called the information paradox. In quantum mechanics, information is conserved. If you know the complete quantum state of a system at one time, you can in principle calculate its state at any other time. The laws are reversible. Information about the past is never truly lost, only scrambled. But what happens to information that falls into a black hole? A book falls in. The book contains information, the words, the arrangement of atoms, the quantum states of all its particles. That information crosses the event horizon and disappears from the observable universe. The black hole grows slightly more massive, but it doesn't record what fell in. Two different books with the same mass leave the same black hole. If the black hole later evaporates through Hawking radiation, the radiation appears to be thermal, random, carrying no information about what fell in. The information seems to have been destroyed. This violates quantum mechanics. It's a paradox. Stephen Hawking initially argued that information is indeed lost, that black holes are exceptions to quantum conservation laws. This position was controversial. Many physicists, including Leonard Susskind and Gerard Hofdorf, argued that information must be preserved somehow, that quantum mechanics is inviolable even for black holes. Over decades, the debate continued. Hawking eventually conceded, announcing in 2004 that he'd been wrong, that information is probably preserved, but the mechanism remains unclear. How does information escape from a black hole? How is it encoded in the Hawking radiation, which appears thermal and random? The leading idea involves the holographic principle. Information about the interior of a black hole might be encoded on its event horizon. The horizon acts like a hologram, a two-dimensional surface that contains all the information about the three-dimensional volume inside. When the black hole evaporates, the information is released in subtle correlations in the Hawking radiation, correlations that are extremely difficult to detect but are present in principle. This idea has profound implications beyond black holes. It suggests that the information content of any region of space is proportional to the area of its boundary, not its volume. Applied to the universe as a whole, it hints that our three-dimensional reality might be a projection from information encoded on a two-dimensional surface at the cosmos's edge. Reality itself might be a hologram, with the bulk of space emerging from information on a boundary. These are deep waters, and we're only beginning to navigate them, but black holes guide us. They're not just astrophysical objects, they're windows into the fundamental nature of reality. Places where our best theories intersect and sometimes contradict each other. By studying black holes, we're not just learning about collapsed stars and galactic centers. We're learning about the fabric of the universe itself, about how space and time work at their most basic level. Another profound implication of black holes involves time. Near a black hole, time dilation becomes extreme. A clock near the event horizon runs slower than a clock far away. This isn't a subtle effect. It's dramatic, measurable, significant. An astronaut orbiting close to a black hole's event horizon might experience a year of subjective time while decades or centuries pass in the external universe. This is real. This is how space-time works, confirmed by countless experiments and observations. Time is not absolute, it's relative, dependent on your motion and the gravitational field you're in. Black holes take this effect to the extreme, making it impossible to ignore. If you could somehow orbit just outside the event horizon of a supermassive black hole, held in place by powerful rockets counteracting the gravitational pull, you could use the black hole as a time machine to the future. You'd orbit for what feels like a year to you, experiencing normal time, aging normally, thinking normally. Then you'd return to distant space to find that decades, centuries, or millennia have passed. This is a one-way trip. You can travel to the future, but never to the past. The laws of physics allow time dilation, but they seem to forbid closed time like curves, paths through space-time that loop back to your own past. Such paths would allow time travel paradoxes. You could go back and prevent your younger self from starting the journey, creating a logical contradiction. Most physicists believe nature finds ways to prevent closed time like curves. Perhaps quantum effects destabilize them. Perhaps classical instabilities destroy the necessary space-time geometries before they can be traversed. Perhaps some principle we don't yet understand forbids them. But the mathematics of general relativity allows them in certain rotating black hole solutions, in wormhole geometries, in some cosmological models. Whether they're physically possible remains an open question. Rotating black holes add even more complexity to the story. A rotating black hole is described by the Kerr solution to Einstein's equations, discovered by Roy Kerr in 1963. Unlike the Schwarzschild solution for non-rotating black holes, the Kerr solution has additional structure. There's the event horizon, still the point of no return. But outside it, there's a region called the ergosphere, where space-time itself is dragged around by the black hole's rotation. Inside the ergosphere, you cannot remain stationary. You must rotate with the space-time. It's like being caught in a whirlpool. You can swim against the current, but you can't stop moving in the direction of rotation. The ergosphere makes possible the Penrose process, named after Roger Penrose, who discovered it in 1969. If you drop an object into the ergosphere and arrange for it to split into two pieces, one piece falling into the black hole and the other escaping, the escaping piece can have more energy than the original object had. You've extracted energy from the black hole's rotation. This sounds like magic, but it's real physics, allowed by general relativity and energy conservation. The black hole has rotational energy. By exploiting the frame dragging in the ergosphere, you can tap into that energy. The black hole spins down slightly, losing angular momentum and rotational energy. That energy goes into the escaping particle. An advanced civilization could potentially harness this. You could construct a system that repeatedly drops matter into the ergosphere, captures the energized debris that escapes, and uses that energy for power. A single rotating supermassive black hole could power a galactic civilization for millions of years, slowly spinning down as its energy is extracted. This is sometimes called a Penrose drive, though it's entirely speculative. We have no idea if any civilization has ever built such a system, but the physics allows it. Rotating black holes might also have different singularity structures. In the Schwarzschild case, the singularity is a point in space and time. In the Kerr case, it's predicted to be a ring, a circle where space-time curvature becomes infinite. And there's a theoretical possibility, though it might be forbidden by physics we don't yet understand, that you could pass through the ring singularity without being destroyed. If you could somehow pass through the ring, the mathematics suggests you'd emerge into another region of space-time, perhaps another universe, perhaps another region of our own universe, far away in space or time. The ring singularity might be a gateway, a connection between different parts of space-time or different spacetimes entirely. This is highly speculative. Most physicists think that quantum effects or classical instabilities prevent anyone from actually traversing the ring singularity. There's a Cauchy horizon inside a rotating black hole, a boundary beyond which the equations of general relativity break down, where predictability fails. The Cauchy horizon might be a place of infinite tidal forces or quantum instabilities that destroy anything trying to cross. Nature might prohibit travel through the ring, even if the mathematics allows it. But the fact that the mathematics allows it is tantalizing. General relativity, our best theory of gravity, predicts structures that could connect distant regions of spacetime, wormholes, Einstein-Rosen bridges, connections between black holes and white holes. These are all solutions to Einstein's equations. Whether they're physically realizable, whether they can be traversed, whether they exist in nature, these are open questions. Black holes also pose questions about the fate of consciousness. If you fall into a black hole, what happens to the information that constitutes you? Your brain states, your memories, your identity, are these preserved somehow, or are they destroyed? If information is preserved, as quantum mechanics suggests, then in some sense you continue to exist, encoded in the quantum state of the black hole, and eventually in the Hawking radiation it emits. But you wouldn't be conscious in any meaningful sense. You'd be information, scrambled and spread across a radiation field. If information is lost, as Hawking initially proposed, then you're truly destroyed. You cease to exist in every sense. Not just dead, but erased, removed from reality more completely than any other form of death. We don't know which is true. We don't even know if the question makes sense. Consciousness might not be the kind of thing that can survive being encoded in a black hole's quantum state. Or it might be. These questions touch on philosophy as much as physics. What does it mean to exist? What does it mean to be conscious? Can consciousness be reduced to information? If so, is that information preserved when you fall into a black hole? Black holes don't answer these questions, but they force us to ask them. They're places where the normal rules break down, where our intuitions fail, where reality itself becomes strange and unfamiliar. Could a black hole destroy the universe? There are speculative scenarios where this might be possible. One involves vacuum decay. Our universe,